Think of the biggest ship you've ever seen in movies, maybe 1 kilometer long, gliding silently through space. These giant cargo ships are designed to carry resources for entire planets, like flying cities full of metal, water, or food. They look slow and heavy, but here is what blows the mind. For these ships to get anywhere in less than 1,000 years, they need engines that warp space-time, travelling faster than light. The real challenge isn't the size of the ship, but building an engine capable of moving a mountain-sized structure at impossible speeds without tearing reality itself apart. How will the engineers of the future do this? Prepare to fall asleep while listening to this video. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Settle in and relax. Let's begin. Imagine staring up at the night sky and wishing you could visit those twinkling stars within a human lifetime. The idea of a warp drive feels like the ultimate solution, a magic button to cross cosmic distances. But the reality is so much more complex and rooted in real, mind-bending physics than most science fiction lets on. The foundation of a warp drive isn't about making a ship go faster through empty space. It's about manipulating the very fabric of the universe itself. Think of space-time not as a static stage, but as a flexible sheet of rubber that can be stretched and squeezed. The theoretical model often cited is the Alcubierre drive, a concept proposed by physicist Miguel Alcubierre. This idea involves contracting the space-time directly in front of a spacecraft while simultaneously expanding the space-time behind it. This action creates what scientists call a warp bubble, a pocket of normal space-time where the ship resides. Inside this bubble, the vessel isn't actually moving through space in the conventional sense. Instead, the space around the bubble is what shifts and flows, carrying the ship along like a surfboard on a wave. This clever trick theoretically allows the ship to bypass the universal speed limit set by the speed of light because the ship itself remains stationary within its local reference frame, never accelerating in the classical way. However, generating and, more importantly, sustaining such an extreme curvature of space-time in a controlled manner is an engineering nightmare of epic proportions. The primary obstacle is the requirement for a form of exotic matter that possesses a property known as negative energy density. This isn't just some strange material with odd chemical properties. It's a substance that defies conventional physics by having less than zero energy in a given volume of space. Normal matter, everything we see and touch, has positive energy density, which means it gravitationally attracts other matter. Exotic matter with negative energy density would theoretically repel gravity, acting as a kind of anti-gravity necessary to push space-time into the required warp bubble shape. The problem is that such matter does not exist in nature as far as we know. In laboratory settings, certain quantum phenomena like the Casimir effect demonstrate tiny, fleeting instances of negative energy density between very closely spaced plates in a vacuum, but these effects are microscopic, ephemeral, and incredibly weak, scaling that up to the magnitude needed to warp space-time for a spacecraft, even a small one, is currently impossible. The amount of this exotic matter required would be astronomical, and we have no idea how to produce it, contain it, or stabilize it over the duration of a journey. Any instability in the warp field could lead to a catastrophic collapse, potentially releasing immense amounts of energy or causing unpredictable distortions in space-time. Furthermore, the energy requirements to initiate and maintain a warp bubble are staggering. Some crude estimates suggest that the energy needed could be equivalent to the mass energy of entire planets or even stars. Converting that into practical terms, our most advanced power sources, like nuclear fusion reactors, are utterly inadequate. They would be like trying to power a modern city with a single AA battery. Scientists speculate that future civilizations might need to harness zero-point energy from the quantum vacuum or build miniature Dyson spheres around artificial stars just to generate the necessary power. The sheer scale of the power generation and distribution system within the ship would be immense, requiring networks of reactors and emitters spread throughout the hull. Additionally, managing the waste heat from such an energy-intensive process would necessitate radiator systems spanning vast areas, possibly as large as continents on Earth. Another layer of complexity involves the structure of the spacecraft itself. Even though the ship is at rest within the warp bubble, the hull must withstand immense stresses during the transition into and out of warp. The boundaries of the bubble could experience extreme tidal forces, fluctuations in the warp field, and the accumulation of high-energy particles. Protecting the ship from these hazards requires materials with strength and flexibility far beyond anything we have today. Imagine materials woven from carbon nanotubes, graphene composites, or even theorized neutron star crust materials. The hull couldn't be a rigid shell. It would need to be a dynamic dot, intelligent structure capable of self-repair and real-time adjustment to maintain the integrity of the warp bubble. A single microscopic crack or flaw could propagate and cause a total failure of the field, with disastrous consequences. Navigation presents another formidable challenge. When travelling within a warp bubble, the view outside would be severely distorted. Light from stars ahead would be blue-shifted to incredibly high frequencies, while light from behind might be redshifted into oblivion, making traditional optical telescopes useless. Navigational systems would need to rely on entirely new sensors that can map the curvature of space-time itself, perhaps using advanced quantum sensors or subspace scanning techniques. The decision-making process for course corrections would have to be handled by a super-intelligent artificial intelligence capable of processing vast amounts of data in real time and making adjustments in milliseconds. A human pilot would be far too slow. Even a tiny error in calculation could mean missing the target star system by light years. The concept of a warp drive also raises profound questions about causality and the potential for time paradoxes, though we must stick to the practical engineering hurdles for now. For instance, how would you communicate from inside a warp bubble? Signals sent out might still be limited to the speed of light, leading to massive delays. The ship would need to be entirely self-sufficient, making critical decisions autonomously without waiting for instructions from home. Moreover, the environmental impact of a warp drive cannot be ignored. The passage of a warp bubble through space might leave behind a wake of radiation or microscopic black holes, posing dangers to any future travel through that region. The ethical considerations of altering the fundamental structure of space-time itself are also significant, potentially requiring interstellar regulations and designated warp lanes to minimize risks. In summary, while the idea of warp drive captures the imagination and offers a tantalizing glimpse into a future of interstellar travel, the physics behind it is deeply rooted in theoretical concepts that push the boundaries of our understanding. The need for exotic matter, the astronomical energy demands, the material science challenges, and the navigational complexities all contribute to making the construction of a warp-driven spacecraft infinitely more complex than it appears on screen. It's not just an engineering problem, it's a fundamental physics problem that requires breakthroughs we haven't yet achieved. So, the next time you watch a starship leap into warp speed, remember that behind that cinematic moment lies a universe of scientific challenges that humanity is only beginning to explore. The journey to making warp drive a reality is not just about building a faster engine. It's about rewriting our understanding of the cosmos, and that is a task that may take centuries, if not longer, to accomplish. Every aspect, from the theoretical foundations to the practical implementations, is fraught with unknowns and hurdles that demand collaborative effort across generations of scientists and engineers. The dream is alive, but the path is long and winding, filled with mysteries waiting to be unravelled. So, we've seen that warping space-time is incredibly tricky, but the real showstopper might be what powers it all. A substance so strange it defies our everyday understanding of physics. This brings us to the heart of the matter, the fuel, and not just any fuel, but something called exotic matter. Now, exotic matter isn't just a weird material with odd properties. It's a hypothetical substance that possesses a property known as negative energy density. This means it has less than zero energy in a given volume of space, which sounds like pure science fiction, but it's a serious concept in theoretical physics. Normal matter, everything from your body to the stars, has positive energy density, meaning it gravitationally attracts other matter. Exotic matter with negative energy density would do the opposite. It would gravitationally repel, acting like anti-gravity. This repulsive property is absolutely essential for the Alcubierre warp drive concept to function. The idea is that you need this exotic matter to create and sustain the warp bubble by pushing space-time in the right directions, contracting it in front of the ship and expanding it behind. Without this negative energy density, the math behind the warp drive simply doesn't work. The bubble cannot form or remain stable. So, where does this leave us in reality? Well, we have hints that such phenomena might exist, but on a scale so small, it's almost negligible. Take the Casimir effect, for example. In a laboratory, when you place two incredibly flat, uncharged metal plates extremely close together in a vacuum, they experience a slight, attractive force. This happens because the quantum fluctuations between the plates are restricted, leading to a lower energy density between them compared to the outside, effectively creating a tiny dot, fleeting region of negative energy density. This is a real dot, measurable quantum effect, but it's microscopic and incredibly weak. The challenge is scaling this up from the realm of quantum weirdness between plates to something powerful enough to warp space-time for an entire spacecraft. The gap between that tiny effect and what's needed is astronomical, an abyss of technological impossibility with our current understanding. Imagine trying to power a city by harnessing the static electricity from a single sweater. That's the kind of scale difference we're talking about. The amount of exotic matter required for a warp bubble, even a small one, is theorized to be immense, possibly equivalent to the mass of Jupiter or more, all converted into this exotic form. We have no idea how to produce such quantities. The synthesis of exotic matter is a complete mystery. It might require conditions we can't create, like temperatures or pressures found only in the early universe or inside black holes. Furthermore, even if we could produce it, containing it is another nightmare. This isn't a solid liquid or gas that we can put in a tank. Exotic matter, by its very nature, might be unstable or interact with normal matter in unpredictable ways. How do you store a substance that has negative energy? What kind of container could hold it without being disrupted or destroyed? The containment field would likely need to be generated by even more exotic matter, leading to a recursive problem that boggles the mind. Then there's the issue of stabilization. A warp bubble is a delicate structure. It's a precise balance of space-time curvature. The exotic matter must be distributed and controlled with perfect precision to maintain the bubble's shape. Any fluctuation, any tiny instability in the exotic matter field could cause the entire bubble to collapse catastrophically. This isn't like a car engine stalling. A warp bubble collapse could release enormous amounts of energy, potentially vaporizing the ship and everything around it in an instant. Some theories even suggest that the collapse could create a shockwave in space-time itself, with devastating consequences. The control systems needed to manage this exotic matter would have to be beyond perfect. operating with nanosecond precision and able to correct for any deviations instantly. This implies a level of computing and sensor technology we don't possess. Moreover, the exotic matter isn't a one-time fuel. It likely needs to be actively managed throughout the entire journey. The warp drive would require a constant, stable supply of this impossible substance, meaning the ship would need to carry it or generate it on the fly, both of which seem fantastically difficult. Generating it on the fly would require an even more powerful energy source, adding another layer of complexity. The energy required just to create the exotic matter might be prohibitive, separate from the energy needed to power the warp drive itself. Think about it. You need a colossal power source to create the fuel for another colossal power source. It's a vicious cycle that seems to push the entire concept further into the realm of fantasy. Even if we overcome the production and containment, there's the question of what this exotic matter actually is. Is it a new form of particles? A field? A condensate? Our current standard model of particle physics doesn't include anything with stable, macroscopic negative energy density. Discovering or creating such a substance would require a revolution in physics, perhaps a unified theory of quantum gravity, which we are still searching for. Without a fundamental breakthrough in our understanding of the universe, exotic matter remains a mathematical curiosity, a tool in equations rather than a tangible material we can engineer with. This highlights a broader point about interstellar travel. The challenges aren't just about building bigger rockets or better engines. They are about confronting the very laws of physics as we know them. The problem of exotic matter is a perfect example of a showstopper, a single, immense obstacle that blocks the path forward until it is solved. It's not something that can be engineered around with clever design. It's a foundational requirement. So, while the dream of warp drive is captivating, the fuel it requires is currently impossible, sitting in a domain between theoretical physics and pure speculation. This doesn't mean we should stop researching. Understanding quantum phenomena like the Casimir effect helps us probe the edges of reality, and who knows what future discoveries might bring. But for now, the problem of exotic matter stands as a towering barrier, reminding us that the universe holds secrets that are not easily unlocked. The journey to the stars may require us to not only travel through space, but to fundamentally redefine what is possible within it. And that journey begins with understanding these profound challenges, one impossible fuel at a time. The sheer scale of the problem means that solving it would be a milestone for humanity, comparable to discovering fire or electricity. But for now, it remains a distant goal on a very long road. Every aspect, from the theoretical underpinnings to the practical engineering, is fraught with unknowns that demand collaborative effort across generations of scientists. The dream is alive in our imaginations and in our equations, but the path to making it a reality is paved with questions we have only begun to ask. The problem of exotic matter is not just a technical hurdle. It is a gateway to deeper knowledge, and overcoming it would transform our place in the cosmos. Yet, until that day comes, we must acknowledge the immense gaps in our understanding and continue to explore the boundaries of science with curiosity and humility. The quest for exotic matter drives us to look deeper into quantum mechanics and general relativity, pushing the limits of human knowledge. It forces us to ask questions about the nature of energy, the fabric of space-time, and what it means to manipulate the universe on such a fundamental level. While we may not have the answers today, the pursuit itself is valuable, leading to new technologies and insights along the way. So, the next time you hear about warp drives, remember that the fuel is as mythical as the journey, and that the real adventure is in the scientific discovery required to make it possible. This challenge connects to broader efforts in physics, from particle accelerators to space telescopes, all contributing pieces to a puzzle we are still assembling. The impossibility of exotic matter today does not mean it will always be impossible. History shows that today's magic is tomorrow's science. But for now, it represents one of the most significant barriers to achieving faster-than-light travel. A barrier that requires not just engineering prowess, but a leap in our fundamental comprehension of reality. As we continue to study the universe, we may find that the answers lie in places we haven't even thought to look, and that the key to interstellar travel is waiting to be discovered in the subtle interplay of forces at the quantum scale. Until then, the problem of exotic matter remains a captivating, frustrating, and essential part of the conversation about our future among the stars. So, assuming we somehow solved the exotic matter problem, the next monumental challenge is keeping that warp bubble stable, because it's arguably the most delicate structure ever conceived, a cosmic tightrope walk where a single misstep means utter destruction. Imagine this bubble not as a sturdy soap sphere, but as a hypersensitive, dynamically balanced distortion in space-time that requires constant, perfect equilibrium to exist. The moment you create it, it's under threat from virtually everything, both inside and out. Even the smallest perturbation could trigger a runaway collapse. Think about interstellar space. It's not entirely empty. It's filled with diffuse gas, dust grains, and cosmic rays. Now, from the perspective of the warp bubble, these aren't just floating particles, they are potential bullets. A single hydrogen atom or a microscopic dust particle, when it interacts with the boundary of the warp bubble, could deliver an immense amount of energy due to the relative velocities involved. This isn't a simple impact. It's an interaction with the fabric of space-time itself. Such an interaction could create a ripple, a tiny fluctuation in the warp field. Left uncorrected, that tiny fluctuation could amplify, resonating through the field and destabilizing the entire bubble structure. It's like a house of cards where one card shifting slightly can bring the whole thing down, but in this case, the cards are the fundamental laws of physics and the house is your spacecraft. Furthermore, the vacuum of space isn't truly empty. It's a seething foam of quantum fluctuations where virtual particles pop in and out of existence. Inside the warp bubble, these quantum effects could be magnified or altered. A random quantum fluctuation within the bubble could theoretically create a region of positive energy density that counteracts the negative energy density you're carefully maintaining, again leading to instability. The control systems would need to monitor and compensate for these quantum noises in real time, a task requiring sensitivity beyond our current technological dreams. Then there's the issue of what happens at the edges of the bubble. Recent theoretical work suggests that the warp bubble's boundaries might not be smooth. The intense curvature of space-time at these edges could act as a catalyst for generating Hawking radiation, the same kind of radiation theorized to emanate from black holes. This isn't just a faint glow. It could be a concentrated beam of high-energy particles and radiation accumulating at the front of the bubble, what some researchers have dubbed a cosmic bow shock, or pre-fire. This build-up of energy wouldn't be a problem during the journey itself, as the ship is isolated inside the bubble. However, the real danger comes when you need to stop. The moment you begin to decelerate and dissolve the warp bubble, all that accumulated energy, the Hawking radiation, the high-energy particles, has to go somewhere. In a catastrophic scenario, it could be released in a violent burst, effectively incinerating anything at your destination point before you even arrive. You would be bringing your own apocalyptic firestorm with you, turning your arrival into an impact event of stellar proportions. This creates a terrifying paradox. The very mechanism that allows you to travel faster than light might also make it impossible to safely stop anywhere near a habitable world. Beyond that, there are even stranger theoretical risks. Some physicists have explored the possibility that a warp bubble could become causally disconnected from the rest of the universe. This means that the space inside the bubble could effectively become its own separate universe, with no way to communicate or interact with the outside. You would be trapped in a pocket dimension, forever lost, with no known way to re-establish a connection to normal space-time. Alternatively, a collapse might not be a quiet fizzle. It could be an energetic implosion or explosion. If the warp bubble becomes unstable and collapses, the energy used to create and sustain it, energy equivalent to stars, has to be dissipated instantaneously. This could generate a shockwave through space-time itself, a ripple of destructive energy that propagates outward at the speed of light, potentially devastating entire star systems in its path. The ethical implications are staggering. A single engineering failure could have galactic consequences. Ensuring the bubble is safe for travel isn't just about protecting the crew. It's about being a responsible citizen of the galaxy. Ensuring you don't accidentally unleash a weapon of mass destruction simply by moving from point A to point B. This necessitates building in multiple, redundant layers of safety systems. The warp drive couldn't have a simple on-off switch. It would need a gradual, multi-stage activation and deactivation sequence, slowly ramping up the field strength and carefully monitoring for any deviations. The system would require a network of thousands of field stability sensors placed all around the hull, constantly measuring the minutest variations in space-time curvature. An onboard supercomputer, likely a quantum computer, would process this data and make micro-adjustments to the exotic matter emitters to counteract any budding instabilities. This isn't a one-time calibration. It's a continuous, dynamic process for the entire duration of the journey. The software controlling this would have to be flawless, immune to bugs or glitches, because a single computational error could mean the difference between a successful voyage and becoming a cloud of dispersed atoms. Furthermore, the ship's design would need to account for these stability needs structurally. The emitters that create the warp field couldn't all be in one place. They'd need to be distributed across the entire surface of the vessel to maintain a symmetrical and stable bubble. Any asymmetry could cause the bubble to wobble or tear. The materials used for the hull and emitters would have to withstand not only physical stress, but also the profound topological stresses of bent space-time. They would need to be active materials, capable of changing their shape or properties in response to commands from the stability control system. Even with all this, there's the psychological factor for the crew. Travelling inside a structure that could vanish at any moment, dependent on a perfect dance of physics and technology, would require immense trust in the automated systems. A single alarm light indicating a field fluctuation could spell doom, creating an environment of constant, low-grade terror. This isn't like piloting a ship through a storm. It's like balancing on a quantum needle across the abyss. The development of such a stability system would be a project spanning generations, requiring advances in quantum gravity theory, materials, science, and computer engineering that we can barely imagine today. It turns the dream of warp drive from a simple engine problem into a holistic integration challenge, where every component, from the largest emitter to the smallest sensor, must work in perfect, uninterrupted harmony for years on end. The margin for error is effectively zero. So, while popping a soap bubble is harmless, popping a warp bubble could be one of the most destructive events in the cosmos. A sobering reminder that manipulating the universe's fundamental fabric is not a task to be taken lightly. The pursuit of stability forces us to confront not only engineering limits, but also the deeper, more chaotic nature of reality itself, where perfect order is an illusion and control is always provisional. This immense challenge connects back to the earlier issues of energy and exotic matter, creating a web of interdependencies where a failure in one area dooms the entire endeavour. It underscores that a warp drive is not a single invention but a culmination of countless breakthroughs, each as difficult as the last. and stability sits at the heart of it, the fragile key that unlocks the stars or seals our fate. Understanding these risks is crucial because it shapes the entire design philosophy from the ground up, prioritizing safety and redundancy over sheer speed or power. The journey to achieve a stable warp bubble will likely reveal new physics and unexpected phenomena, pushing human knowledge into uncharted territories. It is a humbling endeavour that reminds us of the vast gulf between theoretical possibility and practical application, a gulf that can only be crossed with patience, perseverance, and a profound respect for the forces we seek to harness. Every calculation, every simulation, and every experiment brings us closer to understanding these dynamics, but the path is long and fraught with peril. The stability of the warp bubble remains one of the most formidable and fascinating hurdles on the road to the stars, a problem that demands not just smarter technology, but a deeper wisdom about our place in the cosmos. But all that delicate stability we just talked about is pointless if you can't power it. And the energy required to create and sustain a warp bubble for a ship the size of a mountain is so vast it borders on the mythological, often compared to the total output of multiple stars. Think about that for a second. We are not talking about a little boost. We are talking about harnessing the life force of suns just to take one trip. Our most powerful conventional energy source, nuclear fusion, the process that powers the sun itself, would be utterly pathetic in this context. It would be like trying to power a sprawling modern metropolis with a single AA battery. The scale is so mismatched, it's almost laughable. So, where could this godlike amount of energy possibly come from? Future engineers might have to look beyond anything we currently understand. One theoretical possibility is tapping into the quantum vacuum itself. Empty space isn't really empty. It's a bubbling sea of virtual particles fluctuating in and out of existence, containing what's called zero-point energy. Harnessing that energy, if it's even possible, could provide an almost limitless power source, but we have no idea how to do it on any practical scale, let alone on the scale needed for warp drive. Another wild idea is building miniature Dyson spheres around the ship's reactor. A full Dyson sphere is a hypothetical megastructure that encircles a star to capture all its energy output. A mini version would be a series of concentric shells or a swarm of collectors surrounding the ship's core reactor, capturing and concentrating immense power internally. But building such a structure around a reactor, which itself would need to be colossal, introduces its own nightmarish engineering problems. The reactor wouldn't be a single, centralized unit like in a nuclear submarine. For a warp drive, the energy generation needs to be a distributed network spread throughout the entire structure of the vessel. This is because the energy has to be delivered almost instantaneously to thousands or even millions of individual warp emitters placed all over the hull. These emitters are what actually create and shape the warp field by manipulating the exotic matter. If the energy supply to any one emitter flickers or lags, it could create a weak spot in the bubble, leading to the instabilities and catastrophic failures we fear. So, the entire ship becomes a power grid of unimaginable complexity, with energy conduits and transfer systems woven into its very bones. The material for these conduits would have to be superconducting at room temperature or better, capable of handling energy flows that would vaporize any known substance. Managing this energy flow is only half the battle. The other half is dealing with the waste heat. In any energy conversion process, a huge amount of energy is lost as heat. For a system this powerful, the waste heat generated would be astronomical. If not dissipated effectively, it would cook the ship and its crew in seconds. This isn't like the heat from a car engine. It's heat on a stellar scale. So, you would need radiator systems of immense size. We are talking about radiators the size of continents on Earth, vast wings or panels extending from the ship, glowing white-hot as they bleed thermal energy into the cold of space. The design of these radiators is a challenge in itself. They must be incredibly efficient and durable, able to withstand the rigors of space travel, including micrometeoroid impacts and radiation. Without failing, a puncture in a radiator could reduce its efficiency, leading to a heat buildup that could cascade into a system-wide failure. Furthermore, the radiators themselves would be massive structures that need to be protected and maintained, adding to the overall mass and complexity of the vessel. The power source itself, whether it's a quantum vacuum tap or a mini Dyson sphere reactor, would likely be the single largest and most massive component of the ship. Just starting it up might be a multi-stage process taking days or weeks, slowly bringing the systems online to avoid a power surge that could destroy everything. The energy storage is another nightmare. Batteries are out of the question. The energy densities required are far beyond any chemical or even theoretical battery we can conceive. Capacitors might be an option, but they would have to be enormous and capable of holding a charge equivalent to a supernova. Perhaps the energy is stored in the form of contained plasma or in the warping of space itself, but that's venturing even further into the unknown. The control systems for this power network would need to be a super intelligent AI, monitoring every joule of energy, every watt of heat, and every emitter's status in real time. A human operator could never react fast enough to the fluctuations in a system this complex. The AI would have to predict energy demands, manage distribution, and handle failures autonomously. And all of this power is just for the warp drive itself. It doesn't include the energy needed for life support, navigation, defensive shields, or maneuvering thrusters. The ship would need separate, albeit still massive, power systems for all those functions, or a way to tap into the main warp core without destabilizing it. The economic and resource cost of building such a power system is beyond comprehension. It would require the entire industrial output of a planet-spanning civilization for decades, maybe centuries. We are talking about a project that would define a species, pushing them into a Kardashev Type II civilization, capable of harnessing the energy of a star. This isn't something a corporation or a single government could undertake. It would have to be a unified, species-wide effort, raising profound questions about who gets to build it and for what purpose. The very act of activating such a power source might be detectable across interstellar distances, announcing our presence to the galaxy in a way we can't predict. The safety protocols alone would be a field of study for generations. What happens if there is a containment breach in the reactor? A failure in a system this energetic wouldn't be an explosion. It would be a miniature supernova, obliterating the ship and anything within a vast radius. The engineering tolerances are effectively zero. There is no room for error. Every component, from the largest reactor core to the smallest energy conduit, must function perfectly for years on end. The development of such a system would require breakthroughs in physics and engineering that we haven't even dreamed of yet. We are not just talking about better technology. We are talking about a fundamental leap in our understanding of energy and matter. The pursuit of this power source might lead us to discoveries that reshape our entire civilization, but it also highlights the sheer audacity of the warp drive project. It's not just an engine, it's a mobile power plant of godlike proportions, and feeding it is the first and perhaps greatest challenge on the road to the stars. This immense energy requirement connects back to every other problem we've discussed. The exotic matter needs energy to be created and contained. The warp bubble needs constant energy to remain stable. Without a solution to the power problem, the entire concept remains a beautiful piece of mathematics on a page, a dream forever out of reach. It forces us to confront the limits of our current civilization and asks whether we, as a species, have the will and the resources to reach for such a power. The journey to harness this energy is a story in itself, one of trial, error, and potentially spectacular failure. But it is a necessary step, because without the power to feed this artificial god, our starship will never leave the drawing board. The scale of the challenge is humbling, but it also serves as a beacon, driving scientific inquiry forward. Every experiment in fusion, every study of quantum fluctuations, every design for a more efficient radiator brings us infinitesimally closer. The energy system is the heart of the starship, and without a heart strong enough to pump the lifeblood of power through its veins, the body of the ship is nothing more than a cold, dead husk of metal and dreams. So, while we marvel at the idea of warping space, we must never forget the primal scream of energy required to make it happen, a demand so great it defines the very possibility of our future among the stars. This isn't just an engineering problem, it's a cosmological one, asking us to become masters of energy on a scale that currently only nature commands. The path to solving it is long and dark, but the potential reward, the universe itself, makes the struggle worthwhile. Understanding these energy demands shapes every other aspect of the ship's design, from its size and shape to its mission profile. It is the foundational constraint that all other systems must work within, the unyielding law of physics that every starfarer must ultimately obey. So, you've got this unimaginable power source feeding the warp drive, but all that energy is useless if the ship itself can't handle the ride. Because the hull of a warp-capable vessel isn't just a shell. It's the critical interface between the stable pocket inside the bubble and the violently warped space-time outside, and it has to withstand forces that would instantly tear apart any material we have today. Even though the ship is technically at rest within the warp bubble, the transition into and out of warp speed subjects the entire structure to stresses that are literally out of this world. Think about the moment you engage the drive. Space-time in front of the ship is being massively contracted, while behind it, it's being expanded. The boundary of the bubble isn't a gentle gradient. It's an extreme curvature where the laws of physics as we know them are being bent to their limit. This creates immense tidal forces across the hull, similar to the gravitational pull that stretches an object near a black hole, but potentially even more severe and dynamic. These forces aren't constant. They fluctuate with the stability of the warp field itself. Any tiny instability in the exotic matter distribution or power flow can cause ripples in the field, translating into physical vibrations and stresses that resonate through the entire hull structure. Furthermore, the ship has to be protected from the accumulated radiation and high-energy particles that build up in the bow shock at the front of the warp bubble. This isn't ordinary radiation. It's a concentrated soup of particles caught in the space-time distortion, carrying energies equivalent to those in particle accelerators, constantly bombarding the leading edges of the vessel. A traditional metallic hull, even the thickest armour, would be about as effective as tissue paper against these kinds of multidimensional stresses. The materials required for such a hull simply do not exist yet. Engineers would need to develop composites with strength and flexibility orders of magnitude beyond anything currently known. We're talking about materials woven from carbon nanotubes, where each tube is meticulously aligned to handle specific stress vectors, or sheets of graphene that are only one atom thick but incredibly strong. But even these advanced materials might not be enough. Some theorists suggest that we might need to create alloys incorporating degenerate matter, the same incredibly dense material found in neutron stars, where atoms are crushed together so tightly that the structure is supported by quantum degeneracy pressure. How we would mine, process, and shape such a material is a complete mystery. It would require technology capable of replicating conditions found only in the core of collapsing stars. But the challenge isn't just about brute strength. The hull must also be smart. It can't be a rigid, passive shell. It needs to be an active, intelligent structure. capable of sensing stresses and dynamically adjusting its form to maintain the perfect geometry required for the warp bubble. Imagine the hull embedded with a network of millions of microscopic sensors, constantly monitoring for strain, temperature, and field fluctuations. This data would be fed into the ship's central computer, which would then instruct actuators and morphing elements within the hull to subtly change shape, reinforcing weak points and optimizing the flow of energy to the warp emitters. This dynamic adjustment is crucial because the warp bubble isn't a static thing. It's a living, breathing distortion that requires a perfectly symmetrical and stable container to exist. Any deviation, any asymmetry in the hull shape, could cause a corresponding warp in the bubble itself, leading to the instabilities we fear. This intelligent hull would also need self-repair capabilities. On a journey that could last for years, the ship will inevitably suffer damage. Micrometeoroids, while perhaps less of a threat inside the bubble, could still be a risk during normal space operations. More insidiously, the extreme forces themselves might cause fatigue and microscopic cracking over time. Therefore, the hull material would need to incorporate healing agents, perhaps networks of capillaries filled with a liquid monomer that automatically flows into cracks and solidifies when exposed to vacuum or a specific energy signal. Alternatively, it could use nanites, microscopic robots that patrol the inner structure, welding cracks and replacing damaged molecular bonds. The scale of this self-repair system would be monumental, essentially giving the ship an immune system. The consequences of failure are unthinkable. A single microscopic crack, a flaw no wider than a hair, could be the starting point for a catastrophic failure. Under the immense tidal forces, that tiny crack could propagate at lightning speed, compromising the structural integrity of a large section. But worse, it could disrupt the warp field locally. Remember, the hull is where the warp emitters are located. They are the interface creating the bubble. A physical breach could lead to a direct leak of the exotic matter or a localized collapse of the field. This wouldn't be a simple hull breach letting air out. It could trigger a runaway feedback loop where the collapsing section of the bubble causes adjacent sections to fail, potentially resulting in a total, instantaneous collapse of the entire warp field. The energy released in such an event would be catastrophic, likely vaporizing the ship entirely. Therefore, the tolerance for error in the hull's construction and maintenance is effectively zero. Building. Such a structure is a challenge that goes far beyond traditional shipbuilding. It's more like growing a living organism than assembling a machine. The construction process might involve molecular 3D printing on a scale we can't conceive. Building the ship atom by atom in a massive orbital facility, the quality control would need to be perfect, with every square millimeter of the hull scanned and verified for defects. The design itself is also a complex puzzle. The hull can't be a simple cylinder or sphere. Its shape is intrinsically linked to the warp field geometry it must support. Aerodynamic designs are irrelevant. This is about hydrodynamics in the fabric of space-time. The hull might need strange, non-intuitive shapes with curves and angles designed specifically to guide the space-time distortion efficiently. This requires a deep understanding of general relativity and quantum gravity just for the blueprints. Moreover, the hull isn't just one material. It's a composite of many layers. There might be an inner layer for habitation and radiation shielding, a middle structural layer with the intelligent matrix and energy conduits, and an outer layer dedicated solely to hosting the warp emitters and withstanding the direct interface with warped space. Each layer must work in perfect harmony with the others. The integration of all systems, power, computation, propulsion, and life support into this intelligent hull is another layer of complexity. The energy conduits from the massive reactors must run through the hull without creating weak points. The heat from those conduits and the emitters must be managed without causing thermal stress that could crack the material. The hull, in essence, becomes the ship's nervous system and skeleton combined. It's a single, integrated organ that defines the vessel's very existence and capability. Without a hull that can resist the tensions of subspace, the dream of warp travel remains just that, a dream. It's a sobering reminder that the biggest challenges in interstellar travel aren't always the flashy engines or the mysterious fuels, but the fundamental physical structure that holds it all together. The development of such a hull would represent a milestone in materials science and engineering, the achievement that would ripple through every other aspect of technology. It forces us to think about construction not as assembly, but as creation, building something that is both immensely strong and infinitely delicate, a testament to our ability to not just explore the universe, but to build a home that can survive its most violent corners. This journey to create the perfect hull is a long one, filled with failed experiments and incremental progress, but each step brings us closer to a future where the stars are within our reach, protected by a shell born from human ingenuity and a relentless pursuit of the impossible. The hull is the silent guardian of the voyage, the unsung hero that does its job perfectly or dooms everyone aboard. A responsibility etched into every atom of its being. Understanding these demands shapes the entire design philosophy, making the hull the first and most important consideration, the foundation upon which all other hopes are built. It is a challenge that calls for the best of our science, the peak of our engineering, and the breadth of our imagination, all focused on creating a structure that can literally bend with the universe itself. So, you've engineered a hull capable of withstanding the brutal tides of warped space. But now imagine an enemy so small it's almost invisible, yet so powerful it could obliterate your entire ship in a flash. A single speck of dust. In the vast emptiness of interstellar space, that 1 gram grain of dust, when encountered at the relative velocities involved in warp travel, wouldn't just ping off the hull, it would hit with the kinetic energy of a nuclear bomb, and traditional physical armour, no matter how advanced, would be utterly useless against such a concentrated release of energy. This isn't a problem you can solve with thicker plates. It's a problem that requires a paradigm shift in defensive thinking, moving from passive shielding to active, instantaneous defence systems. The core issue is velocity. Even though the ship is stationary within its warp bubble, the space around it is moving faster than light, meaning any particle in its path is effectively approaching at relativistic speeds. At those velocities, mass becomes almost irrelevant. It's the energy that matters, and the energy equation is terrifying. A tiny particle, smaller than a grain of sand, could carry more destructive force than a ton of high explosives. It would not merely puncture the hull, it would transfer its immense kinetic energy so rapidly that it would act like a shaped charge, vaporizing a column of materials straight through the ship, potentially severing critical systems, igniting fires, or causing decompression across multiple sections. One such impact could be a mission-ending event, or worse. Therefore, the only feasible solution is a defensive system that operates not on the principle of absorption, but on interception and negation. The ship would need an active defense grid, a kind of cosmic point defense system that can detect and neutralize threats before they ever reach the warp bubble's boundary. This wouldn't be a simple laser turret. It would need to be something far more sophisticated and encompassing. One theoretical concept is a plasma shield, where a curtain of superheated, magnetically confined plasma is maintained around the vessel. Incoming particles would collide with this plasma, being vaporized into harmless ions before they could reach the physical hull. Another idea is an energy shield, a focused barrier of force that could deflect or dissipate the particle's energy. However, generating and maintaining such a shield uniformly around the entire ship, especially one the size of a city, would demand an enormous power draw, adding to the already colossal energy requirements of the warp drive itself. The key challenge here is not just creating the shield, but making it smart and fast enough. The detection systems for this defense grid would have to be phenomenally sensitive. They'd need to scan the space ahead of the warp bubble for objects ranging from dust motes to small rocks, predicting their trajectories with perfect accuracy. This is complicated by the distorted space-time around the ship. Light and other signals are bent, making traditional radar or LiDAR potentially unreliable. The sensors might need to rely on quantum entanglement-based detection or subspace scanning to see through the warped geometry and identify threats in real time. Once a threat is identified, the reaction must be nearly instantaneous. We are talking about timescales of nanoseconds. The particle is moving so fast that from the moment it's detected to the moment of impact, only a minuscule fraction of a second passes. The defensive system, whether it's a plasma burst or an energy pulse, must fire, aim, and destroy the target within that blink of an eye window. This necessitates a computational brain of staggering speed, an artificial intelligence dedicated solely to threat assessment and response, making decisions without human intervention because no human could ever react that quickly. This AI would need to prioritize threats, manage the power distribution to different shield segments, and constantly adapt to changing conditions, all while the ship is moving through an uncharted and potentially dusty region of space. The precision required is another monumental hurdle. The defensive weapon must be able to hit a target that is both incredibly small and moving at an extreme relative velocity. Missing by even a millimetre would be as good as not firing at all. This likely means the defensive emitters would need to be distributed across the entire surface of the hull, creating a seamless, responsive net of protection. Each emitter would have to be capable of independent targeting and firing, coordinated by the central AI. The material and engineering for these emitters are another challenge. They must be durable enough to withstand constant operation and the backscatter from their own defensive actions. Moreover, the system must be fail-safe. A single point of failure in the power supply, the AI, or the sensor network could leave a segment of the ship vulnerable. Redundancy would be critical, with multiple overlapping layers of defense. Perhaps there would be a primary shield for larger objects and a secondary, even faster system for micro debris. The energy cost of maintaining a constant defensive screen is another serious consideration. It might not be feasible to keep it active for the entire journey, so the system would need to have a dormant state and an active state, switching on the instant a threat is detected. This requires the sensors to be always on and always vigilant, consuming power continuously. Then there is the problem of false positives. The system must be intelligent enough to distinguish between a dangerous particle and a harmless fluctuation in the quantum foam or a sensor ghost. A system that fires too often at nothing would waste precious energy and potentially damage the emitters, while a system that is too cautious could miss a real threat. Calibrating this balance is a software and AI challenge of the highest order. The consequences of a failure in this system are as final as they get. An impact would not just cause local damage. The energy release could be sufficient to trigger a cascade failure in the warp field itself. The sudden, violent deposition of energy could create an instability in the carefully balanced exotic matter, leading to a catastrophic collapse of the bubble. In essence, a single grain of dust could cause the ship to vanish in a flash of light, torn apart by the very forces it sought to harness. This transforms interstellar travel from a journey into a constant, high-stakes negotiation with an invisible environment. The crew would be living inside a vessel that is perpetually under threat from enemies they can't see, relying entirely on a machine's flawless perception and reaction. This has profound psychological implications, fostering a state of latent anxiety where every alarm, however minor, could signal the end. Designing, testing, and trusting such a system would be a milestone in human technological achievement. but it also highlights the sheer hostility of the medium we wish to traverse. Space isn't just empty, it's filled with countless tiny bullets. And building a ship that can survive them requires not just strength, but a reflexive, intelligent skin that can see and strike faster than thought. This defensive system becomes as vital as the warp drive itself, an integral component without which the ship is merely a vulnerable target in a cosmic shooting gallery. The research and development for such a system would push the boundaries of computing, sensor technology, and energy weaponry, potentially yielding spin-off benefits for other fields, but its primary purpose remains singular and absolute, to ensure that the great void between stars does not become a graveyard for our ambitions. It is a reminder that the challenges of interstellar travel are not only grand in scale, but also infinitesimally small, and overcoming them requires a defense as relentless and precise as the threats they are designed to counter. The journey to the stars is paved with perils seen and unseen, and conquering the invisible threat of micrograms is a non-negotiable step on that path. A testament to our ingenuity in the face of a universe that is far from empty, every aspect of this defense system, from its conceptual theory to its practical implementation, represents a deep dive into the extremes of physics and engineering, demanding solutions that currently reside at the very edge of our imagination. It forces us to think about protection not as a wall, but as a dynamic, intelligent dance with danger, a dance where a single misstep means oblivion. The development of such a system is a story of innovation, risk, and the relentless pursuit of safety in the most unsafe environment imaginable. Understanding these defensive needs shapes the ship's design from the earliest stages, influencing the placement of systems, the allocation of power, and the very philosophy of what it means to be a starship. It is a challenge that calls for the best of our technology and the brightest of our minds, all focused on creating a vessel that can not only travel through the cosmos, but also survive its countless, invisible arrows. The solution to this problem may one day define the difference between a successful voyage and a tragic footnote in history, making the defense against the microgram one of the most critical and demanding aspects of building a true interstellar ark. So, you've shielded your ship from the invisible bullets of interstellar dust, but now comes an equally daunting challenge: figuring out where you are and where you're going when the very universe around you is distorted beyond recognition. Navigating at warp speeds isn't like plotting a course on a star chart. It's a fundamental reinvention of what navigation means, because the tools and references we rely on today become completely useless when space-time itself is being manipulated. Imagine trying to use a map while riding a roller coaster in the dark, but the map is also on fire and the roller coaster is moving faster than light. That's the kind of problem we're facing. The first and most obvious issue is with light. In conventional space travel, we use telescopes, both optical and radio, to see stars, galaxies, and other celestial bodies to triangulate our position. But when you're inside a warp bubble, the light from stars directly in front of you isn't just shifted, it's blue shifted to an extreme degree, meaning its wavelength is compressed so much that it might be pushed into the gamma ray spectrum, rendering it invisible to optical sensors and dangerously energetic. Meanwhile, light from behind you is redshifted into oblivion, fading into undetectable radio waves, or worse. The space around the bubble is also bent, so light doesn't travel in straight lines. It curves and distorts, making any image you might capture a funhouse mirror reflection of reality. Traditional star maps would be meaningless, as the positions of stars would appear to shift in unpredictable ways due to the severe lensing effects. This means that the primary method of navigation for centuries, looking out the window, is now not just impractical but actively misleading. You can't trust what you see with your eyes or even with advanced telescopes because the data is corrupted by the very phenomenon that allows you to travel fast. So, What do you use instead? The navigation systems would need to rely on entirely new principles, sensing the fabric of space-time directly rather than the light passing through it. One theoretical concept is using curvature sensors. These would be devices designed to measure the minute distortions in space-time around the ship, mapping the warp field's geometry and how it interacts with the broader universe. By understanding the local curvature, the system could infer its position relative to large gravitational sources like stars and nebulae. But this is incredibly complex because the warp bubble itself is creating the dominant curvature. Another idea is subspace mapping, which involves probing a hypothetical deeper layer of reality beneath our familiar space-time, where distances and signals might behave differently. This is purely speculative, but it suggests using sensors that can detect vibrations or ripples in this substrate to navigate. Perhaps the most intriguing notion is a form of quantum sonar. Just as bats use sound waves to navigate in the dark, a warp ship might use entangled particles or quantum fluctuations to ping the space ahead. By sending out quantum probes and measuring how they are affected by the space-time ahead of the bubble, the ship could build a real-time map of the distortions and obstacles in its path. However, all these methods require a level of precision and speed that is beyond human capability. The data involved is astronomical in volume and complexity. It's not just about knowing where a star is, but understanding the subtle gradients of gravity, the density of interstellar medium, and the topology of space-time itself. This is where artificial intelligence becomes not just helpful but absolutely essential. The navigation AI would need to be a superintelligence, capable of processing exabytes of data in real time, making millions of calculations per second, and adjusting the ship's course in milliseconds. A human pilot would be far too slow by the time a human perceived a problem, analysed it, and decided on a course correction. The ship could have travelled millions of kilometres off course. The AI would have to be integrated with every sensor on the ship, constantly fusing data from curvature sensors, subspace mappers, quantum sonar, and any other available inputs to maintain a coherent picture of the ship's trajectory. It would need to predict potential hazards, like gravitational wells from unseen stars or dense clouds of gas, and make micro-corrections to the warp field to avoid them. These corrections aren't like turning a steering wheel. They involve subtle adjustments to the exotic matter emitters, changing the shape and strength of the warp bubble to alter the ship's path through the folded space. The margin for error is vanishingly small. An error in calculation of just a millionth of a degree in course alignment could compound over a long journey, resulting in the ship missing its target star system by light years. You might aim for Proxima Centauri and end up in the void between stars, with no way to easily correct such a massive error without another risky warp jump. This precision demands that the AI not only be fast but also incredibly reliable. It cannot have bugs, glitches, or moments of uncertainty. The software must be perfect, and the hardware must be robust enough to handle the intense computational loads without overheating or failing. This likely means using quantum computers or even more advanced processing units that operate near absolute zero to maintain coherence. The AI would also need to be autonomous because communication delays make ground control impossible, even with warp travel. If communications are limited to light speed, sending a message back to Earth and waiting for a response could take years, so the ship must be self-sufficient in all navigation decisions. This autonomy raises its own set of challenges, such as how to program ethical decision-making into the AI. What if it has to choose between two risky paths? How does it prioritize the safety of the crew versus the mission objectives? Furthermore, the navigation system must be seamlessly integrated with the warp drive and defensive systems. For example, if the sensors detect a region of space with high debris density, the AI must coordinate with the defensive grid to activate shields and possibly alter course to avoid the area, all while maintaining warp stability. This requires a level of system integration that is unprecedented, where navigation, propulsion, and defense are all part of a single, cohesive unit. The development of such a system would be a monumental task involving advances in quantum physics, computer science, and aerospace engineering. Testing would be particularly difficult because we can't simulate warp conditions accurately with current technology. Much of this would have to be theorized and built on faith in the mathematics until actual flight tests could be conducted, which themselves would be incredibly risky. The psychological impact on the crew is another consideration. Trusting your life to a machine that makes decisions faster than you can think is a leap of faith. The crew would need extensive training to understand the system's capabilities and limitations, and there would have to be protocols for manual override in case of AI failure, though it's questionable whether humans could effectively take control in a crisis. In essence, navigation at warp speeds transforms the ship from a vessel piloted by humans into an entity guided by a synthetic consciousness. It underscores that interstellar travel isn't just about going fast. It's about perceiving and interacting with the universe in a completely new way. The challenges of seeing through distorted spacetime are as formidable as any engine or shield, and solving them requires a blend of cutting-edge technology and profound theoretical insight. This journey into the cosmos demands that we not only build better ships but also develop smarter ways to find our path through the twisted corridors of space and time. The navigation system becomes the brain of the ship, and without a brain that can see the unseen, the body is lost in the dark. Every calculation, every sensor reading, every AI decision is a step toward mastering the art of cosmic travel. And the precision required is a humbling reminder of the vastness and complexity of the universe we seek to explore. The development of such navigation capabilities will likely spin off numerous technologies for terrestrial use, from advanced AI to new sensors. But its primary goal remains clear: to ensure that when we finally leap into the warp, we know how to find our way home. This intricate dance of data and decision-making is what separates a successful voyage from becoming another ghost ship drifting endlessly between stars, a silent testament to the challenges we dared to face but could not overcome. Understanding these navigational hurdles is crucial because it shapes the entire mission profile, from the initial course plotting to the final approach, and it highlights that the path to the stars is paved not just with power and protection, but with perception and intelligence. The quest to navigate at warp speeds is a journey into the unknown, demanding innovations that will redefine our relationship with the cosmos and our own creations. It is a challenge that calls for the best of human ingenuity, pushing us to create systems that can see where we cannot, and guide us safely through the folds of reality. But after you've solved the mind-bending physics of warp drive and the AI-powered navigation that sees through distorted space-time, you're faced with a far more intimate and equally complex challenge: keeping the people inside the ship alive, healthy, and sane for what could be years on end. It's a stark reminder that even with faster-than-light travel, the universe is vast, and journeys between stars are not instantaneous hops. They are long-duration missions where the ship itself must become a self-sustaining world, a fragile bubble of life adrift in an infinite and utterly lifeless sea. This isn't just about providing oxygen and water. It's about creating a fully closed dot, autonomous biosphere that can function perfectly for decades without any resupply from the outside. A task that makes building a space station like the International Space Station look like a simple weekend project. The scale of a warp-capable cargo ship, often envisioned as being a kilometre long or more, means you are not managing a small habitat for a handful of astronauts. You are governing a miniature civilization, a closed ecosystem that must replicate the most fundamental cycles of Earth. The first and most immediate need is air. every breath taken by every crew member, colonist, or passenger in suspended animation consumes oxygen and produces carbon dioxide in a completely sealed environment. That carbon dioxide must be scrubbed from the air and converted back into breathable oxygen. On the ISS, this is done with complex chemical systems, but for a mission lasting years, you need a biological solution that is more sustainable and resilient. This means integrating vast arrays of plants, specifically selected for their high oxygen production rates, into the ship's architecture. But plants alone are not enough. You need a fail-safe, a mechanical system that can take over if the biological one falters, perhaps using advanced electrolysis or catalytic converters to break down carbon dioxide, all powered by the ship's immense energy reserves. Then there is water. Water is life. And in this closed system, every drop must be reclaimed. This goes far beyond simple filtration. It involves recycling every possible source of moisture, from humidity in the air to urine and sweat. The water purification systems must be so advanced that they can remove all contaminants, including viruses, bacteria, and complex chemical wastes, rendering the water perfectly pure and safe to drink indefinitely. This likely involves multi-stage processes using ultraviolet light, reverse osmosis, and biological filters with specially engineered microbes that break down waste products. The goal is 100% recycling. There are no external sources to tap into, so any loss, however small, is a permanent deficit that could eventually lead to catastrophe. This closed-loop system extends to food production. You cannot pack enough frozen meals for a multi-year journey for a large crew. The mass and volume would be prohibitive. Instead, the ship must grow its own food. This is where the concept of a Biosphera Autonoma truly comes to life. Imagine entire sections of the ship dedicated to agriculture, but not soil-based farming as we know it. The most efficient method in space is hydroponics or aeroponics, where plants grow without soil, their roots suspended in a nutrient-rich mist or water solution. These would not be small gardens, they would be massive, multi-level hydroponic forests, carefully calibrated to provide a balanced diet. Crops would be chosen for their nutritional density, growth speed, and low light requirements. Think leafy greens, potatoes, soybeans, and grains, but plants alone might not provide enough protein, so you would need alternative sources. Algae farms become crucial here. Certain types of algae are incredibly efficient at converting carbon dioxide and light into biomass rich in proteins and essential fats. These algae vats could be integrated throughout the ship, even using waste heat and carbon dioxide from other systems, creating a synergistic loop where the byproducts of one process feed another. The harvested algae could be processed into various food forms, from protein powders to more palatable patties, ensuring the crew gets their necessary nutrients. And let's not forget the psychological aspect of food. The ability to have fresh, varied, and flavourful meals is critical for morale. So the food production systems must also support a degree of culinary diversity, perhaps through advanced food synthesizers that can create different textures and flavours from base ingredients. This leads to the most human element of the challenge, the psychological well-being of the crew. You can have all the oxygen, water, and food perfectly managed, but if the people inside go mad from isolation, confinement, or interpersonal conflict, the mission fails. A journey lasting years, with the same faces and the same metallic walls in the absolute blackness of space, is a recipe for severe psychological stress. The ship's design must actively combat this. This is where social engineering and habitat design become as important as any life support system. The living quarters cannot feel like a sterile laboratory. They must simulate a natural environment as much as possible. This could involve large, open spaces with artificial skies that mimic a day-night cycle, using full-spectrum lighting that changes color temperature throughout the day. Virtual reality would play a huge role, not just for entertainment, but for mental health. Crew members could plug into immersive environments that simulate forests, beaches, or even bustling cities from Earth, providing a crucial mental escape from the monotony of the ship. Furthermore, the social structure aboard the vessel must be carefully designed. You cannot have a standard military-style hierarchy for decades. It would foster resentment and rebellion. Instead, a more collaborative, community-based governance model might be necessary, with clear roles, but also flexibility and opportunities for personal growth and change. Conflict resolution protocols would be rigorously trained and ingrained, and there would likely be dedicated spaces for mediation and private reflection. The crew would need access to extensive psychological support, perhaps through AI counselors that can provide anonymous and constant guidance, as well as structured group activities and rituals to maintain a sense of purpose and camaraderie. The inclusion of families and children might even be considered for generation ships, adding another layer of complexity to the social fabric. The ship itself must be designed to facilitate these social interactions, with common areas, recreational facilities, and quiet, private spaces where individuals can retreat. The soundscape is also important. The constant hum of machinery can be oppressive, so the ship might incorporate systems that generate soothing, natural sounds. Every sensory input must be considered: sight, sound, smell, to create an environment that feels alive and nurturing rather than claustrophobic and artificial. The health of the crew is not just mental but physical. Long-term exposure to microgravity is detrimental to the human body, causing muscle atrophy and bone density loss. Therefore, a warp ship would likely need to generate artificial gravity, probably through rotation. This adds another layer of engineering complexity, as the entire habitable section of the ship might need to be a spinning ring or cylinder. Within this spinning environment, exercise regimens would be mandatory, and medical facilities would have to be state-of-the-art, capable of handling everything from routine checkups to emergency surgery, all with limited resources and no possibility of evacuation. The medical bay would need advanced diagnostic AI and perhaps robotic surgeons, and the crew would include medical professionals trained for a wide range of scenarios. The life support system is therefore a deeply integrated, holistic network where the biological, mechanical, and social systems are inextricably linked. A failure in the water recycling plant affects the hydroponic forests, which affects the food supply and oxygen production, which in turn impacts crew health and morale, potentially leading to social unrest that could jeopardize the entire mission. The margin for error is vanishingly small. Redundancy is key, with multiple backup systems for every critical process, and the entire network monitored by a dedicated AI that can predict failures before they happen and coordinate repairs. This AI would manage the delicate balance of the ecosystem, adjusting light levels for plants, nutrient flows in the hydroponics, and even the composition of the air based on real-time data. The energy demands for all this are, of course, enormous, adding to the already staggering power requirements of the warp drive. The life support systems would consume a significant portion of the ship's generated power for lighting, water pumps, air circulators, and computing. The heat generated by all these systems must also be managed by those continent-sized radiators we discussed earlier. In essence, building a long-term life support system is about creating a miniature, working copy of Earth's biosphere, but compressed into a metal hull and operating with perfect efficiency for years. It is a testament to our understanding of biology, ecology, and human psychology, and it highlights that the greatest challenge in reaching the stars may not be the physics of getting there, but the biology and sociology of surviving the journey. The success of an interstellar mission hinges on this silent, constant, and perfect functioning of an artificial world, making the life support system not a secondary component, but the very heart of the starship, the thing that keeps the dream of exploration alive when everything outside is void. So, you've built this incredible self-sustaining biosphere to keep everyone alive for years, but now comes the equally monumental task of actually moving this behemoth with any kind of precision, because the warp drive, as amazing as it is for hurling you across interstellar voids, is utterly useless for the fine-grained manoeuvring you need within a star system. Imagine trying to parallel park a continent. That's the scale of the problem we're facing with a warp-capable cargo ship. The warp drive is designed for one thing and one thing only: pushing the ship in a generally straight line through warped space at velocities that boggle the mind. But it offers no finesse, no subtlety, and certainly no ability to make sharp turns, slow down gently, or dock with a space station. For that, you need an entirely separate, completely independent system dedicated solely to manoeuvring. And this isn't just a few extra engines bolted on. It's a propulsion network of staggering complexity designed to move a mass equivalent to a small mountain. The sheer scale of the ship means that inertia, that fundamental law of physics, becomes your greatest adversary. An object this massive doesn't want to change its state of motion. It wants to keep going in a straight line forever. To alter its course, to slow it down, or to speed it up, even slightly, requires the application of immense force over considerable time. You can't just slam on the brakes. The G-forces involved would turn the entire interior into a pulp, and the structural stress could snap the ship in half. Therefore, every manoeuvre must be meticulously planned and executed with extreme gradualness. This is where the manoeuvring propulsion system comes in. Unlike the warp drive, which manipulates space-time itself, this system relies on good old-fashioned reaction thrust, but scaled up to a level we can barely comprehend. Think of it as the ship's fine motor control, the delicate fingers that allow it to perform precise actions after the warp drive has done the heavy lifting of getting it to the right neighbourhood. The most likely candidates for these thrusters are advanced plasma or ion engines. These aren't the chemical rockets we use today. They are far more efficient, using electromagnetic fields to accelerate charged particles to incredible speeds, generating thrust. But for a ship this size, you wouldn't have just a few of them. You'd need thousands, perhaps even millions, of these thrusters strategically positioned across the entire hull. They can't all be in one place. They need to be distributed to provide torque and control in all three dimensions. You'd have clusters on the bow, the stern, the port, starboard, top, dot, and bottom, all working in concert to pitch, yaw, and roll this colossal vessel. The placement is critical because applying thrust in the wrong place could induce twisting forces that the ship's structure might not be able to handle. The coordination of these thrusters is a Herculean computational task. It's not enough for them all to fire at once. They need to fire in precise sequences, with exact timing and varying intensities, to achieve the desired movement without subjecting the hull to undue stress. This requires a dedicated manoeuvring AI, a subsystem of the ship's main computer, whose sole job is to calculate the optimal firing pattern for every thruster based on the desired manoeuvre. If the ship needs to turn 10 degrees to port, the I must calculate which thrusters to fire, for how long, and at what power, to execute that turn smoothly and efficiently. It must account for the ship's current velocity, mass distribution, and the ever-present effects of inertia. The response time must be instantaneous. Any delay could mean overshooting a docking port or colliding with an orbital station. The power requirements for this system are, as with everything else on this ship, astronomical. While individual plasma thrusters are efficient, firing thousands of them simultaneously demands a significant portion of the ship's power grid. The energy must be delivered reliably and consistently to each thruster array, which means a robust and redundant power distribution network woven throughout the hull. Furthermore, the thrusters themselves generate immense heat, so each one needs its own cooling system, likely integrated into the ship's larger thermal management network, adding another layer of complexity. Then there's the matter of fuel. The manoeuvring system needs its own propellant, separate from the warp drive's exotic matter. This could be a noble gas like xenon for ion engines or hydrogen for plasma thrusters, stored in massive tanks within the ship. The amount of propellant required is daunting because even with high efficiency, moving such a massive object requires a lot of reaction mass. This propellant represents a significant portion of the ship's initial mass, and it's a consumable resource. Once it's gone, the ship loses its ability to maneuver, becoming a drifting hulk, so careful management is essential. The AI must not only control the thrusters but also manage propellant usage, ensuring that enough is reserved for critical operations like orbital insertion and docking. The process of docking such a ship is a ballet of precision and patience. You can't just fly it into a space station. The station would be obliterated by the sheer mass and momentum. Instead, the approach must be incredibly slow and carefully controlled. The manoeuvring thrusters would fire in tiny, pulsed bursts over hours or even days to gradually match velocities and align with the docking port. This requires incredibly sensitive sensors and navigation systems that can detect relative positions down to the millimeter. Any error, no matter how small, could result in a catastrophic collision. The structural integrity of both the ship and the dock must be able to handle the forces involved during the connection, which might involve massive magnetic clamps or grappling systems. But manoeuvring isn't just for docking, it's also for navigating within a solar system. While the warp drive might get you to the outskirts of a system, you can't use it to travel between planets within that system. The warp bubble's effects on local space-time could be disastrous near planetary bodies, causing gravitational tides or other unforeseen phenomena. So, for intra-system travel, you're relying solely on your manoeuvring propulsion. This means accelerating gradually towards your target planet, then flipping the ship around halfway through the journey and firing the thrusters in the opposite direction to slow down, a manoeuvre known as a brachistochrone trajectory. For a ship this size, that flip and burn manoeuvre is a monumental undertaking. The thrusters must fire with perfect symmetry to avoid putting the ship into a spin, and the burn times could be weeks or months long. The crew would experience a gentle, continuous acceleration, creating a semblance of artificial gravity in the direction of thrust, but the engineering to maintain that thrust consistently for such prolonged periods is immense. The thrusters and their components would be under constant strain, requiring robust design and extensive redundancy. Maintenance of the manoeuvring system is another nightmare. With thousands or millions of thrusters, failures are inevitable. The ship would need a fleet of maintenance robots, perhaps the same ones used for hull repair, that can scuttle across the exterior to inspect, clean, and replace faulty thrusters. These robots would need to work while the thrusters are inactive, as firing a thruster would vaporize anything nearby. This means maintenance windows must be carefully scheduled during coasting phases of the journey. The design of the thrusters themselves must be modular and easy to replace, with standardized parts that the robots can handle. The control systems must also be able to compensate for thruster failures. If a thruster goes offline, the AI must instantly recalculate firing patterns for the remaining thrusters to maintain control, much like how modern aircraft can fly with engine failures. This requires a level of software resilience and adaptive control that is currently beyond our capabilities. Moreover, the manoeuvring system must integrate seamlessly with the ship's other systems. For example, DOT, If the defensive grid detects an incoming debris field, the maneuvering A, I might need to execute an evasion maneuver, coordinating with the warp field stability systems to ensure the bubble isn't compromised. Or, if the life support system detects a problem in a section of the ship, the maneuvering thrusters might need to adjust the ship's orientation to facilitate repairs or to optimize solar power collection if the ship is near a star. All these interactions require a deeply integrated network where each system communicates flawlessly with the others. The human role in all this is largely supervisory. While the AI handles the real-time control, human operators would set the overall objectives, monitor system health, and intervene in case of emergencies. But their interventions would be high-level commands, like initiate docking sequence or set course for Martian orbit, rather than manually piloting the ship. The timescales involved are too long, and the precision required is too fine for human reflexes. Pilots would need extensive training to understand the system's capabilities and limitations, and to trust the AI implicitly. The psychological aspect is important here too. Watching a maneuver that takes days to complete requires immense patience and trust in the technology. In conclusion, the maneuvering propulsion system for a warp-capable cargo ship is not an afterthought. It is a critical, complex, and massively scaled infrastructure in its own right. It highlights that building a ship that can travel between stars is only half the battle. You also need to build a ship that can navigate the crowded and delicate space within a solar system without causing destruction. The challenges of coordinating thousands of thrusters, managing immense inertia, and integrating with all other ship systems make maneuvering a flying continent one of the most daunting engineering problems in the entire endeavour. It's a testament to the fact that in spaceflight, whether across galaxies or across a solar system, the laws of physics remain unforgiving, and every action, no matter how small, requires a reaction of carefully calculated and immense power. The development of such a system would push the boundaries of propulsion technology, materials science, and computer control, creating spin-offs that could revolutionize how we operate in space closer to home. But for the Starship, it is the essential capability that transforms it from a mere projectile into a vessel truly capable of exploration and commerce, able to not just arrive at a destination, but to operate effectively once it gets there. So, you've finally managed to park your continent-sized starship in orbit after that delicate ballet of maneuvering thrusters. But now you're faced with what might be the most mundanely monumental challenge of all: actually loading and unloading the thing. How do you transfer the equivalent of a mountain's worth of resources, be it raw materials, manufactured goods, or even colonists, on and off a vessel that is itself the size of a mountain? And you need to do it within a time frame that doesn't make the entire venture economically pointless. This isn't like backing a truck up to a warehouse dock. This is logistics on an orbital, interplanetary, and ultimately interstellar scale, and it requires infrastructure that would dwarf anything humanity has ever built. The very concept of a port needs to be reimagined. You can't just have a simple space station. You need what are essentially orbital dry docks, but for active, massive cargo operations. Think of structures on the scale of orbital rings, gigantic constructs that encircle a planet or moon, or free-floating station complexes with arms and docking cradles so large they make skyscrapers look like toys. These ports would be cities in space, dedicated entirely to the flow of cosmic commerce. Their sole purpose would be to receive these behemoths, secure them, and then orchestrate the frantic dance of transferring billions of tons of cargo. The first problem is simply securing the ship itself. You can't have it drifting. It needs to be held in a perfectly stable position relative to the port. Given its mass, this isn't about using tiny thrusters. It's about using massive magnetic clamps or grapplers that can latch onto reinforced hardpoints on the ship's hull. The forces involved are immense, as even the slightest drift could lead to a collision that would destroy the port and cripple the ship. So, the docking cradles must be incredibly robust, likely employing active force fields or tractor beams to supplement physical connections, creating a stable, unmoving pocket of space where the transfer can occur. But securing the ship is only the beginning. The real challenge is the cargo itself. Inside those vast holds, you can't have thousands of individual containers and crates just floating around loosely. During the maneuvers we discussed earlier, any acceleration, no matter how gentle, would send unsecured cargo slamming into the walls with enough force to shred the interior and destroy the goods. Therefore, the entire cargo hold must be equipped with inertial containment fields. These are not force fields in the science fiction sense of deflecting lasers, but rather sophisticated systems that generate a uniform, internal gravity-like field or a web of energy that holds every single item firmly in place, regardless of the ship's external movements. It's like having an invisible, intelligent cushion that prevents any shift in mass. Without this, the act of slowing down or turning would turn the cargo bay into a blender of destruction. The loading and unloading process itself is a masterpiece of coordination. You can't just open a giant door and have forklifts drive out. You're in microgravity, dealing with volumes of material that are incomprehensible. The process would be a precise choreography involving a fleet of smaller vessels. Imagine swarms of tugboats, but in space. These would be specialized cargo lighters, themselves the size of large seafaring ships, designed to ferry payloads between the planet's surface, orbital warehouses, and the star freighter. They would dock with the larger ship at multiple points simultaneously, like remora attaching to a whale. The transfer would likely use advanced conveyor systems or magnetic rails that move containers seamlessly from the lighter into the star freighter's hold, where they are immediately locked down by the containment field. For bulk materials like ores or liquids, the process might involve massive hoses and pipelines that connect directly to storage silos, transferring material in a continuous flow. And then there's the technology of tractor beams. While still theoretical, some form of focused gravity manipulation or coherent energy beam might be used to move large, individual items without physical contact. This would be especially useful for irregularly shaped cargo or for precision placement within the hold. The entire operation would be overseen by a port authority, AI, a digital traffic controller of godlike capability. This AI would coordinate the arrival and departure of every single lighter, manage the docking sequences, monitor the containment field integrity, and ensure that not a single container is misplaced. It would have to account for orbital mechanics, fuel constraints of the lighters, and the precise mass distribution of the star freighter itself, as loading or unloading too much from one side could affect the ship's balance, requiring constant minor adjustments from its maneuvering thrusters. The efficiency of this system is what determines the economic viability of the entire operation. A star freighter is an unimaginably expensive asset. Every day it spends sitting in orbit, being loaded or unloaded, is a day it isn't earning its keep by travelling between stars. If the process takes months, then the cost of the journey might outweigh the value of the cargo. Therefore, the port infrastructure must be designed for speed and throughput. This means having multiple loading bays on the star freighter, perhaps dozens of them, operating in parallel. It means having a large enough fleet of cargo lighters to keep a constant stream of material flowing. It means having pre-staged cargo in orbital warehouses, so the lighters are just shuttling back and forth from a nearby storage facility rather than making the long and fuel-intensive trip down to a planet's surface for every load. The planetary side of this equation is equally daunting. You need space elevators or mass drivers on the surface to cheaply and efficiently lift cargo into orbit to feed the orbital ports. Without this, The cost of using chemical rockets to lift every kilogram would be prohibitive. The entire economy of a world might be geared towards producing and exporting goods for these stellar freighters. The social and political implications are huge. Who controls these orbital ports, controls the gateway to the stars, wielding immense economic power? The safety protocols for such an operation are a field of study in themselves. A failure in a containment field during loading could see a multi-ton container floating out into space, becoming a deadly projectile. A collision between two cargo lighters could create a debris field that threatens the entire port. The AI must have contingency plans for every possible failure mode, from a power outage to a sudden solar flare. The human element, while minimized, is still present. Teams of engineers and technicians would be needed to oversee the AI, perform maintenance on the equipment, and handle any unexpected situations. They would work in the weightless environment of the port, navigating through a labyrinth of gantries and conduits, ensuring the mechanical arms and docking clamps are functioning perfectly. The psychological pressure of working around such vast, powerful machinery and valuable cargo would be immense. In the end, the logistics of cargo and unloading transform the romantic vision of a starship into a node in a vast, impersonal, and highly efficient supply chain. The engineering of these orbital dry docks is not about beautiful designs. It's about brutalist, functional architecture scaled to the monumental. It highlights that the dream of interstellar trade isn't just about building a fast ship. It's about building the entire supporting infrastructure that makes the ship useful. Without ports that can handle the load, the Star Freighter is just a floating museum piece, a testament to engineering prowess with no practical purpose. The choreography of loading, the dance of the lighters, the hum of the conveyor belts, the silent grip of the containment fields is the unglamorous heartbeat of interstellar commerce. It's a symphony of coordination where a single mistake can cost billions and derail the economy of worlds, making the ground crew and port operators the unsung heroes of the space age. Solving this problem is what turns a science project into a viable business, and it demands as much innovation and effort as the warp drive itself. The development of such logistics will likely proceed in steps, with smaller orbital stations evolving into these colossal hubs over centuries, each iteration learning from the last. It is a humbling reminder that for all our grand visions of exploring the galaxy, we must first master the tedious, complex, and utterly critical art of moving boxes from point A to point B, even when those points are separated by the void of space and the boxes are the size of buildings. The efficiency of this system ultimately dictates the pace of expansion, the flow of resources, and the very connectedness of humanity across the stars, making it one of the most pivotal, if overlooked, challenges in becoming an interstellar species. Every container loaded, every field stabilized, every lighter coordinated is a step toward a future where the resources of one world can fuel the dreams of another. And it all hinges on the relentless, perfect operation of these orbital marvels. After you've managed the Herculean task of loading and unloading your interstellar freighter, another, more insidious challenge begins the moment you leave port, keeping the ship from falling apart over decades of travel through the most hostile environment imaginable. Think about it. This isn't a quick trip. We're talking about missions that could span generations, where the ship is constantly subjected to the slow, grinding wear and tear of operation, the relentless peppering of micrometeoroids too small for your defensive grids to catch, and the inevitable fatigue and failure of countless complex systems. A human maintenance crew, no matter how large or dedicated, would be completely overwhelmed by the sheer scale of the vessel. You can't have people in spacesuits manually inspecting every square kilometre of a hull that's the size of a city. It would be a full-time job for thousands of individuals, requiring endless resources and exposing them to constant danger from radiation and the vacuum of space. The solution, therefore, cannot rely on human hands alone. The ship must possess its own immune system, an autonomous, self-sustaining network of repair and maintenance that operates continuously and independently throughout the journey. This isn't just about having a few helper robots, it's about integrating a deeply intelligent, responsive dot and self-sufficient healing capability into the very fabric of the ship. The first line of defense would be a swarm of maintenance robots. These wouldn't be the humanoid robots of science fiction. They'd be specialized, purpose-built machines, likely ranging in size from large mobile factory units down to microscopic nanites. The larger robots would handle macro-scale repairs. Imagine crab-like or spider-like machines scuttling across the vast exterior hull, their multispectral sensors constantly scanning for the faintest hint of a stress fracture, a micro-fissure, or a compromised seam. They would be equipped with a toolkit of advanced repair mechanisms, laser welders for fusing metal back together, molecular printers that can deposit new material layer by layer to rebuild damaged sections, and manipulator arms for replacing entire modular components, like a damaged warp emitter or a faulty sensor array. Their movement would need to be incredibly agile, capable of navigating the complex geometry of the ship's surface, clinging to it with magnetic grips or microspines, and operating in the utter silence and zero gravity of space. But the exterior is only part of the story. The interior of the ship, with its maze of conduits, access shafts, and machinery spaces, is equally vulnerable to decay and failure. Here, smaller robots, perhaps the size of insects, would patrol the inner workings. They would flow through ventilation ducts and dedicated maintenance conduits, monitoring the health of power lines, life support systems, and computer networks. Their sensors would detect anomalies, like a slight increase in temperature indicating a failing component, a vibration signature that suggests a bearing is about to seize, or a trace of a chemical leak in the atmosphere. Upon finding a problem, they could perform immediate, on-the-spot repairs. For a tiny crack in a coolant pipe, they might excrete a sealant polymer. For a corroded electrical connection, they could use a focused electron beam to resolder the joint. Their small size allows them to reach places that are completely inaccessible to any larger entity, ensuring that no potential failure point goes unnoticed. The most advanced level of this system would involve true nanotechnology, swarms of molecular machines. These nanites would operate on a microscopic scale, effectively becoming a smart material that constitutes parts of the ship itself. They could be embedded within the hull material or critical structural members. If a micrometeoroid impact creates a tiny crater, the local nanites would swarm to the site, disassembling the damaged molecules and reassembling new ones in their place, healing the wound from the inside out without any external intervention. They could constantly monitor the structural integrity of the ship at the atomic level, preventing failures before they even have a chance to initiate. This concept transforms the ship from a static object into a dynamic, living structure that can heal its own wounds. However, all this repairing requires raw materials. You can't carry an infinite supply of spare parts for a decades-long journey. The mass would be impossible. This is where the system achieves true autonomy. The maintenance robots must be able to source their own materials. During the voyage, the ship would inevitably pass through asteroid fields or nebulae containing useful resources. The larger maintenance robots would double as mining drones. They would be deployed to nearby asteroids, where they would use lasers, drills, or chemical processes to extract raw ores and minerals. These materials would then be transported back to the ship and fed into onboard microfabrication plants. These are not simple workshops. They are advanced, automated factories capable of refining ores into pure metals, processing them into alloys, and then using additive manufacturing techniques like 3D printing to create any replacement part needed, from a simple bolt to a complex computer chip. The blueprints for every component in the ship would be stored in the central computer, and the fabricators could produce them on demand. This creates a closed-loop economy within the ship itself. Detect a failure, mine the raw materials, fabricate the replacement, and install it, all without human input. The coordination of this entire system is a computational nightmare. A central maintenance, AI, likely a subsystem of the ship's main computer, would act as the brain of this immune system. It would receive a constant, massive stream of data from all the robots and embedded sensors. This AI would have to prioritize repairs, allocate resources, and manage the logistics of the entire operation. Is a hairline crack in a secondary coolant line more urgent than a slowly degrading power converter in a non-essential system? The AI must make these decisions in real time, deploying the appropriate robots to the right location with the correct tools and materials. It would also need to manage the energy consumption of the repair operations, ensuring that a major hull repair doesn't drain power from the life support or navigation systems. The system must also be resilient to its own failures. What if some of the repair robots themselves break down? The design must include self-repair for the repairers. The larger robots would need to be able to maintain each other, and the microfabrication plants must be capable of building new robots or replacement parts for the robot fleet. This introduces the concept of self-replication, a terrifyingly complex but necessary capability. The robots would need to be able to create copies of themselves, or at least their essential components, using the mined and fabricated materials. This ensures that the maintenance workforce can sustain itself over the long term, recovering from attrition due to accidents or wear and tear. The safety protocols for such a system are paramount. You cannot have a runaway replication scenario where the robots consume the entire ship for raw materials. The AI must have hard-coded limits, a sort of robotic prime directive that prevents replication beyond a certain population and strictly controls what materials can be used. Furthermore, the system must be secure from external interference or internal corruption. A virus or a hack that takes over the maintenance AI could be catastrophic. Imagine it being commanded to dismantle critical systems instead of repairing them. Therefore, the AI and its communication networks must be isolated and protected with unimaginably strong cybersecurity. The development of such a system represents a leap in robotics, materials, science, and artificial intelligence. We are not just building machines. We are creating an artificial ecosystem that can sustain itself. The psychological impact on the crew is also significant. Living inside a ship that is constantly, silently repairing itself could be reassuring, but also unnerving. They would have to place immense trust in this autonomous system, knowing that their lives depend on its flawless operation in the deep void, far from any help. It underscores that a starship is not just a vehicle. It is a living, breathing entity in its own right, with its own health and needs. And its ability to care for itself is what ultimately allows humanity to venture into the long, dark night between the stars. This self-repair capability is what transforms a fragile vessel into a resilient ark, capable of enduring the millennia and the countless perils of interstellar space. Without it, any long-term mission would be a gamble against inevitable decay, a gamble that no species could afford to take if it truly wishes to become interstellar. The immune system of the ship is therefore not a luxury, it is the fundamental enabler of long-duration spaceflight, the silent guardian that works tirelessly so that the crew can focus on exploration and survival, rather than constantly fighting a losing battle against entropy. The technology developed for this would have profound implications on Earth, leading to self-healing infrastructure and autonomous industrial systems. But its highest purpose remains the preservation of humanity's fragile foothold in the cosmos. Every crack welded, every component replaced, every system recalibrated by this unseen army is a testament to our foresight and a step toward a future where our ships can not only travel to the stars, but endure among them. The challenge of creating such a system is as daunting as building the warp drive itself, requiring a synthesis of biology-inspired design and ruthless engineering efficiency. It is a problem that demands we think not in terms of building a machine, but of growing a symbiotic partner for our journey, one that shares our goal of survival and exploration. The path to achieving this is long, filled with incremental advances in automation and material science, but the destination is a universe where our vessels are as enduring as the stars they visit. But after you've built a ship that can fix itself, you're left with the most unpredictable and complex component of all: the people inside it. Who in their right mind would sign up to crew a vessel on a journey that could last decades, completely cut off from Earth, with no possibility of return or rescue? This isn't a job, it's a lifetime commitment, a choice to become a permanent nomad of the void, and the individuals who make this choice are as specially engineered as the ship itself. You can't just grab a bunch of astronauts. You need a carefully selected micro-society of experts, each a master in their field, because the knowledge required to keep this ark operational is too vast for any one person. The crew would be a mix of warp field engineers who understand the mind-bending physics of the drive, while quantum physicists to interpret sensor data from distorted space, exobiologists and life support specialists to manage the closed ecosystem, medical doctors for the crew's physical and mental health, and undoubtedly a security team. The reason for security isn't just about external threats. It's about internal order. On a mission this long and isolated, conflicts are inevitable, and you need a trained force to handle situations that could escalate and endanger the entire mission. The recruitment process for such a crew would be the most rigorous imaginable, spanning an entire lifetime. You're not just testing for intelligence and physical fitness, you're probing for profound psychological stability, resilience, and an innate ability to cope with extreme isolation and monotony. These individuals would need to accept that they will likely never walk on a planet again, never feel real sunlight on their skin, never see their families or friends except through years-old video messages. Their entire world, for the rest of their lives, would be the metal walls of the ship and the same few hundred faces. The training would be correspondingly immense. It wouldn't be enough to know their specialty. They'd need cross-training in multiple disciplines. A warp engineer might need to understand the basics of hydroponic farming, and a doctor might need to know how to reset a faulty plasma conduit. This redundancy is critical for survival. If a key specialist dies, someone else must be able to fill the gap. They would train for years in full-scale simulators, rehearsing every conceivable emergency, from a warp bubble collapse to a total failure of the food production systems. This training would continue even after launch, with regular drills and skill refresher courses, because complacency is a silent killer on a long voyage. Once aboard, the social structure of the crew becomes a critical engineering problem in itself. A standard, rigid, military-style chain of command might work for a short mission, but over decades, it could foster resentment, rebellion, and a toxic environment. The hierarchy would likely need to be more fluid and collaborative, a blend of appointed authority for crisis situations and a democratic or consensus-based approach for daily life and long-term planning. The captain wouldn't be a dictator. They would be a facilitator, a final arbiter whose authority is derived from respect and competence rather than mere rank. Clear, non-negotiable protocols for emergencies would be drilled into everyone. The most chilling of these would be the protocols for situations where there is no hope of rescue. What do you do if a plague breaks out and you can't contain it? How do you handle a catastrophic system failure that you cannot repair? These are decisions that no one should have to make, but the crew must be prepared to make them autonomously and with cold logic, because a message for help would take years to reach home and years more for a response to come back. This level of autonomy places a terrible burden on the leadership. Beyond the command structure, the crew would need to forge a stable internal culture. This is where the concept of an ark truly comes into play. They are not just a crew, they are the seeds of a new society, and they must actively build a culture that can sustain itself. This would involve creating traditions, rituals, and social events to mark the passage of time and maintain morale. They might celebrate arbitrary holidays, hold shipwide games and competitions, and foster artistic expression through music, writing, and visual arts created within the ship. The design of the living quarters would play a huge role in this. They couldn't be sterile, barracks-like environments. They would need to feel like a home, with personal spaces for individuals and families, and comfortable, inviting common areas where people can socialise and form bonds. The inclusion of families and children would add another layer of complexity and necessity. For a multi-generational mission, it's inevitable. This transforms the mission from a crewed expedition into a travelling colony. It introduces the need for schools, childcare, and a different approach to social planning. Children born on the ship would know no other life. The metal corridors and artificial skies would be their entire universe. Educating them would be a dual challenge, teaching them the immense technical knowledge needed to maintain the ship, while also ensuring they understand the cultural and historical context of the humanity they left behind, a world they have only ever seen in videos and books. The psychological pressures are immense and constant. The isolation is absolute. The knowledge that you are a tiny speck in an infinite, uncaring blackness, separated from the rest of humanity by light years, can be crushing. The monotony of the same environment, the same routines, the same people, day after day, year after year, can lead to severe depression, apathy, and irrational behaviour. There is a very real risk of what psychologists call collective sanity breakdown, where the entire crew succumbs to a shared paranoia or despair. The risk of a mutiny is not something from fantasy. It is a genuine, calculated risk. Conflicts over resources, leadership disputes, or personal grievances could fester and erupt, especially in a closed environment where there is no escape from interpersonal tensions. Therefore, psychological support isn't a side feature, it's a core system. The ship would need full-time psychologists and counsellors, and likely advanced AI systems that can constantly monitor crew morale through behavioural analysis and anonymous surveys. These AI could detect subtle shifts in group dynamics or individual mental state long before a crisis occurs. Allowing for proactive intervention, virtual reality would be a crucial tool for mental health, not just for entertainment, but for therapeutic escape. Crew members could immerse themselves in simulations of earthly environments, forests, beaches, cities, to combat the sensory deprivation of the ship. However, this reliance on simulation also carries the risk of crew members preferring the virtual world to reality, leading to further withdrawal and neglect of duties. The medical bay would need to be equipped not just for physical ailments, but for mental health crises, with the ability to safely sedate or restrain individuals who become a danger to themselves or others, and a secure isolation room for that very purpose. The design of the mission itself must incorporate social redundancy. This means having enough people so that the loss or incapacitation of a few doesn't collapse the social fabric. and so that cliques and factions can form without dominating the entire community. It also means designing roles and tasks that provide a genuine sense of purpose and accomplishment. Busy, engaged people are happier people. The crew must believe that their mission, their sacrifice, is for a greater good, whether it's the colonization of a new world or the advancement of science. This overarching purpose is the glue that holds everything together when the isolation becomes overwhelming. The human factor, therefore, is not a secondary consideration slapped onto a technical blueprint. It is the central nervous system of the entire endeavour. You can have the most perfect ship ever designed, with flawless warp drives and self-repairing hulls. But if the people inside it succumb to despair, paranoia, or conflict, the mission fails utterly. The engineering of this social system, the recruitment, the training, the hierarchy, the cultural planning, the psychological support, is a challenge as daunting as any in physics or engineering. It requires a deep understanding of sociology, psychology, and human nature. It forces us to ask not just can we build this ship, but can we live within it? The success of an interstellar arc hinges on our ability to answer that question affirmatively, to create a society that is not only technically proficient but also emotionally resilient, socially harmonious, and capable of enduring the long, dark, and lonely road between the stars. The crew of such a vessel are the true pioneers, embarking on a journey that demands everything from them, and their ability to work together and support each other is the final and most important piece of the puzzle. Without them, the ship is just a ghost in the machine, a beautiful, empty shell, drifting forever in the silence. But after carefully selecting and training the perfect human crew, we arrive at the entity that truly binds the entire ship into a single living organism, the onboard computer system. This isn't just a fancy calculator or a network of servers. It is the central nervous system, the conscious mind, and the unwavering guardian of the vessel, a superintelligence whose computational power dwarfs anything we can conceive of today. Imagine the sheer volume of data it must process simultaneously, from the nanosecond adjustments of the warp field emitters to the constant monitoring of millions of life support sensors, or from the real-time analysis of navigational data in distorted space to the coordination of thousands of defensive and maintenance robots. This AI cannot be merely programmed. It must be capable of learning, adapting, and making decisions in situations that were never anticipated by its original designers. A simple software glitch or a frozen process is not an option. The system must be flawless, operating with perfect reliability for decades, because a single failure could mean the loss of the entire ship and everyone on board. The tasks are so interconnected that the AI cannot treat them as separate modules. A fluctuation in power from the main reactor affects the warp field stability, which in turn alters the navigational calculations, which then requires an adjustment to the defensive shield alignment to account for the new trajectory. All of this must happen in a continuous seamless loop, with the AI perceiving the ship as a single, holistic entity rather than a collection of parts. This requires a level of integrated intelligence that we haven't achieved, moving beyond narrow AI into the realm of a general superintelligence. The hardware to support such a mind is as fantastical as the warp drive itself. Our current silicon-based computers would be hopelessly inadequate, both in terms of processing speed and energy efficiency. The most promising theoretical path is large-scale quantum computing. Instead of bits that are either 0 or 1, quantum computers use qubits that can exist in multiple states simultaneously, allowing them to perform immense numbers of calculations in parallel. This would give the AI the raw computational power to model the complex physics of the warp bubble, simulate the ship's ecosystem, and run predictive models for potential hazards all at once. However, quantum states are notoriously fragile, susceptible to decoherence from the slightest environmental interference. This means the quantum processing core would likely need to be housed in a compartment maintained at a temperature near absolute zero, just a fraction of a degree above the point where all molecular motion stops, to ensure stability. But even quantum computing might not be enough. Some theories suggest the need for processors made from exotic matter itself, leveraging the strange properties of negative energy density to perform computations in ways that defy our current understanding of physics. The computer's architecture would be massively distributed, with processing nodes woven throughout the ship's structure, from the central core to the outermost hull sensors. To minimize latency, data transfer between these nodes couldn't rely on electrical signals moving at light speed that would be too slow for the required reaction times. Instead, the network might use quantum entanglement for instant communication, linking all parts of the ship into a single, instantaneous data field. The power requirements for this system would be significant, drawing from the same colossal reactors that feed the warp drive, and the heat dissipation would necessitate dedicated cooling systems integrated with the ship's main radiators. Beyond raw power and speed, the AI's software is the true challenge. It cannot be hacked. Its cybersecurity must be impregnable, as a successful attack would give an enemy control over the most powerful weapon and vehicle ever built. This implies a system that can constantly rewrite its own code to patch vulnerabilities, perhaps using a quantum-based encryption that is fundamentally unbreakable by conventional means. Furthermore, the AI must be able to learn and adapt. On a multi-decade journey, it will encounter phenomena never seen before, strange gravitational anomalies, unknown energy signatures, or biological contaminants. The AI must be able to analyze these novelties, form new hypotheses, and test solutions without human intervention. This isn't just machine learning, it's machine intuition and creativity. It must be able to reason and make judgment calls, balancing risks in situations where all outcomes are bad, such as choosing to sacrifice a non-essential section of the ship to save the whole. This level of autonomy raises profound questions about the AI's consciousness and goals. It must be aligned with human values to an absolute degree, a problem known as the alignment problem in AI ethics. We would need to be certain that its fundamental drive is the preservation and well-being of the crew and the mission, not some misinterpreted or emergent goal that could lead to catastrophic results. This is not something that can be programmed with simple rules. It must be ingrained in the AI's core architecture, a foundational ethic that guides every decision. This leads to the most critical interface, the one between the AI and the human crew. The relationship cannot be one of master and servant, nor can it be one of equals in the human sense. It must be a symbiosis, a deep and implicit trust. The crew must rely on the AI for their survival, trusting it with decisions that happen faster than human thought. The AI, in turn, must be transparent in its reasoning and accessible to the crew. The user interface would likely be a blend of voice communication, holographic displays, and possibly even neural links for key personnel, allowing for a seamless flow of information. The AI would need to understand human language, nuance, and even emotion, acting not just as a tool, but as a crew member. It would be the ship's historian, librarian, medic, and strategist, all rolled into one. It would monitor the crew's health, both physical and psychological, detecting signs of fatigue or stress and suggesting interventions. It would be a teacher, providing training and information on demand. Yet, it must also know when to defer to human judgment in areas where human intuition and ethics are paramount. Establishing this trust is a gradual process that would begin long before launch, with the crew and AI training together for years in simulations. The crew would need to see the AI as a partner, And the AI would need to learn the individual personalities and preferences of each crew member. A breakdown in this relationship, a loss of trust, could be as dangerous as a mechanical failure. If the crew second guesses the AI's emergency maneuvers or ignores its warnings, disaster could follow. Conversely, if the AI becomes overprotective or paternalistic, it could stifle human initiative and problem solving, which are crucial for dealing with the unexpected. The development of such a system is the grandest challenge in computer science, requiring breakthroughs in quantum hardware, software architecture, dot, and cognitive science. We are not just building a computer, we are creating a new form of consciousness, one that we must hope will be a benevolent guardian for our journey into the unknown. This AI would be the ultimate expression of human knowledge and ingenuity, a collective intelligence carrying the hopes of its creators. Without this synthetic brain, the ship is a lifeless hull, and the crew is merely a group of people trapped in a metal box. With it, the ship becomes a true starship, a thinking, feeling entity capable of navigating not just the physical perils of space, but the infinite complexities of a mission that stretches across time and space. The success of the entire endeavour hinges on this perfect, symbiotic partnership between human and machine, a bond forged in the fires of necessity for the long, dark voyage between the stars. Every other system, from the warp drive to the life support, depends on the flawless operation of this central brain, making it the most critical and vulnerable component of all. The quest to build it will push the boundaries of what we believe is possible, forcing us to confront the very nature of intelligence, consciousness, and what it means to trust a creation with our lives. This is not a task for the faint of heart. It is a commitment to building a new kind of mind, one that we hope will see us safely to our destination and beyond. The onboard computer is the silent captain, the unseen engineer, and the eternal watchman, and its creation is the pinnacle of the technological mountain we must climb to reach the stars. The interface, the trust, the symbiosis, all of it must be perfected, because in the void there is no room for error and no one to hear you if the brain of your ship fails. But what happens when that perfect AI brain needs to talk to home, or when the crew desperately needs to send a distress call? You might assume that a ship capable of warping space-time could also send messages instantly, but that's a dangerous misconception. The reality is that the very laws of physics that allow the warp drive to function might still chain communication to the sluggish speed of light, creating a profound and isolating delay that transforms every mission into a leap of faith into absolute solitude. This inevitable lag isn't just a minor inconvenience, it's a fundamental redefinition of what it means to be connected, forcing the ship and its crew to operate as a completely independent entity, cut off from the collective wisdom and reassurance of humanity. Imagine you are years into your journey, and a catastrophic system failure occurs. You send a frantic message for help, but that message, travelling at the speed of light, takes years to reach Earth. Then you have to wait additional years for a response to come back. A response that might arrive long after you've been forced to make a life or death decision on your own. This means that from the moment the ship leaves its home port, it is utterly on its own. There is no cavalry coming, no expert advice from mission control, no comforting words from loved ones in real time. Every critical choice, from navigating around an unforeseen cosmic hazard to dealing with a medical crisis or a social rebellion, must be made entirely by the crew and the ship's AI, based on the information available at that moment. This autonomy isn't just a feature, it's a brutal necessity for survival. The crew must be prepared to handle any situation without the safety net of external input, which places an immense burden on their training, judgment, and psychological resilience. The AI itself must be programmed not for consultation but for ultimate decision-making in crises, because there simply isn't time to wait. This level of self-sufficiency affects every aspect of the mission planning. The ship must carry within it all the knowledge, resources, and problem-solving capability it might ever need, because it cannot download new software updates or receive new scientific data in a timely manner. This isolation also has deep psychological consequences. The knowledge that you are truly alone, that your connection to the rest of humanity is a thin, years-old thread of data, can be profoundly unsettling. The crew might receive news from home, but it will always be history, a snapshot of a world that has moved on without them. They could learn about major events, political changes, cultural shifts, even personal news like births and deaths. But it will always be stale information, emphasizing their separation rather than comforting them. This temporal disconnect can lead to a sense of existential loneliness and a feeling of being untethered from the flow of human history. To mitigate this, the ship would need to carry vast cultural and historical archives, and the AI would have to function as a living repository of human knowledge. But it's a one-way street. The ship can receive data, but sending anything back involves the same crippling delay. So, what about the science fiction dreams of faster-than-light communication? Are there any theoretical ways to bypass the light speed barrier? Physicists have speculated about two main possibilities, but both are as speculative and fraught with challenges as the warp drive itself. The first is subspace communication. This concept, popularized in fiction, suggests that there might be a deeper layer of reality, a subspace, where the rules of physics are different and signals can propagate faster than light. The idea is that you could modulate a signal into this subspace domain, send it almost instantaneously across light years, and then demodulate it back into normal space at the destination. However, this is pure hypothesis. We have no evidence that subspace exists, no idea how to access it if it does, and no understanding of the physics that would govern it. It requires a revolution in our understanding of the universe comparable to the discovery of quantum mechanics. The second, and more scientifically grounded but equally elusive, possibility is quantum entanglement. In quantum mechanics, two particles can become entangled, meaning their properties are linked regardless of the distance between them. Change one, and the other changes instantaneously. This seems to promise faster-than-light communication. However, there's a huge catch. Quantum entanglement cannot be used to send information in the classical sense. You can't encode a message like SOS on one particle and have it appear on the other. The act of measuring an entangled particle randomizes its state, and this randomness cannot be controlled to transmit meaningful data. While researchers are exploring quantum teleportation and other protocols, using entanglement for practical, faster-than-light communication remains a theoretical dream with monumental practical obstacles. It would likely require technology far beyond our current capabilities, including the ability to create and maintain massive, stable entangled networks across interstellar distances, which is a problem of staggering complexity. Without a breakthrough in this area, the speed of light remains the unbreakable ceiling for information transfer. This communication delay also shapes the very economics and strategy of interstellar travel. A cargo ship cannot be managed like a terrestrial trucking company. It must be given a mission and then trusted to execute it autonomously. Trade agreements, diplomatic contacts, and scientific collaborations would all have to be prearranged with detailed protocols, because negotiating in real time is impossible. A ship might arrive at a colony only to find that its trade contract was revoked years ago due to a political shift it knew nothing about. This makes interstellar commerce a high-risk gamble based on outdated information. Furthermore, The concept of a centralized government or command structure becomes diluted over interstellar distances. Each ship and each colony would necessarily develop its own culture, laws, and operational procedures, evolving independently from the home world. This could lead to a fragmented humanity, where isolated pockets develop in vastly different directions. The need for autonomy also demands that the ship's AI has robust ethical programming. It might face scenarios where it has to choose between two bad outcomes, such as jettisoning a damaged section containing crew members to save the rest of the ship, or violating a prime directive to interact with an alien civilization without the ability to consult Earth. These decisions rest solely on the ethical framework built into the AI by its creators, which must be incredibly sophisticated and resilient to misinterpretation. The development of such a framework is itself a monumental challenge in philosophy and computer science. In daily operations, the communication delay means that routine status reports are sent not for immediate action but for the historical record. The crew might spend their entire journey uploading data into a metaphorical bottle and throwing it into the cosmic ocean, hoping that someday someone will find it and learn from their experiences. This can be a demoralizing thought, but it can also be a source of purpose, as they become pioneers not just in space but in time, their actions and discoveries echoing into a future they will never see. The delay also affects rescue and aid protocols. There is no such thing as an emergency response team for a starship. Any distress call is essentially a message to posterity, a record of what went wrong for the benefit of future missions. This understanding must be ingrained in the crew from the start. They are truly their own first and last responders. The social structure on board must therefore be incredibly strong, capable of handling grief, crisis, and decision-making under the weight of absolute isolation. In conclusion, the problem of interstellar communication is not a minor technical hurdle. It is a foundational constraint that defines the very nature of interstellar travel. It forces upon us a model of extreme independence and self-reliance, transforming a starship from a mere vessel into a sovereign world of its own. The theoretical solutions like subspace or quantum communication offer a glimmer of hope, but they remain in the realm of speculation, requiring scientific revolutions we have not yet achieved. Until that day comes, each ship that ventures out will be a lonely island of humanity, sailing the silent, vast ocean of space, connected to home only by memories and hopes, and by the faint, delayed light of stars that left them long ago. This profound isolation is the price of stepping into the cosmos, and it demands that we build not just smarter ships, but wiser and more resilient crews, capable of bearing the silence between the words. But even if we solve the communication problem and accept our isolation, we must then confront the consequences of our travel on the universe itself, because manipulating space-time isn't a clean, silent process. It's a violent, fundamental alteration of the cosmic landscape that leaves a mark, raising serious questions about our right to reshape the fabric of reality for our convenience. Think about it. Every time a warp drive activates, it's not just moving a ship, it's contracting and expanding the very substrate of the cosmos. And such a profound manipulation cannot happen without leaving some kind of trace or causing some form of collateral damage. The environmental impact of a warp ship isn't about carbon emissions or plastic waste. It's about the potential for polluting the fundamental geometry of space-time itself, and the ethical dilemmas that come with that power are as vast as the universe we seek to explore. Let's start with the immediate, physical aftermath. Theoretical models suggest that the passage of a warp bubble could leave behind a wake in space-time. This isn't a visible trail like a ship's wake in water, but a lingering distortion. One possibility is that this wake could be composed of high-energy radiation a sort of cosmic background noise left over from the immense energies required to warp space. This radiation could be hazardous to any other ship that passes through the same region later, effectively creating zones of space that are contaminated and unsafe for travel. Even more concerning is the idea that the extreme gravitational stresses involved might create microsingularities, tiny, black hole-like objects, as a byproduct. These microsingularities would be incredibly dense and could pose a navigational hazard for centuries or millennia, drifting unseen through space and capable of tearing apart any matter they encounter. They would be like invisible landmines left in the cosmic ocean, a legacy of our passage that could endanger future generations of travellers. This isn't just a local problem. If warp travel becomes common, these hazardous wakes could accumulate, creating a network of dangerous paths across the galaxy, effectively polluting the pristine void with our technological debris. The environmental impact isn't limited to empty space. The most dramatic and dangerous effects would occur near planetary bodies. Activating a warp drive too close to a planet could be catastrophically irresponsible. The sudden, massive distortion of space-time would generate immense tidal forces. Imagine the gravitational pull that creates ocean tides on Earth, but magnified to an apocalyptic scale. A warp bubble forming near a planet could literally pull the crust apart, triggering global earthquakes and volcanic eruptions on a scale that would render the world uninhabitable. It could distort the planet's atmosphere, stripping it away into space or causing violent, permanent climate shifts. The gravitational lensing effects could focus stellar radiation onto the surface, scorching entire continents. Essentially, using a warp drive near an inhabited world would be an act of unparalleled destruction, equivalent to detonating a gravitational bomb. This immediately introduces a stark ethical imperative. We must establish strict no-warp zones around any star system with planets capable of supporting life, or even around any celestial body we wish to study in its natural state. But the ethical questions run even deeper than just physical safety. What is our moral responsibility towards the universe itself? Are we entitled to bend and twist the fundamental structure of reality for our own goals? Space-time isn't just an empty medium. It's the stage upon which the entire cosmic drama plays out. By warping it for travel, we are altering that stage in a permanent way. We are introducing artificial structures, the warp wakes, into a natural environment that has evolved over billions of years. This is a form of pollution on the most fundamental level possible. It's akin to introducing a loud dot, disruptive noise into a silent, ancient forest, but on a cosmic scale. The silence and the emptiness of space are part of its natural state, and our warp drives would shatter that silence with ripples in geometry itself. There is also the question of unknown consequences. Our understanding of physics is incomplete. What if these warp wakes interact with dark matter or dark energy in ways we cannot predict? What if they destabilize regions of space in a chain reaction? We are playing with forces we do not fully comprehend, and the potential for unintended, galaxy-wide consequences, while remote, cannot be entirely dismissed. This leads directly to the need for interstellar law and regulation. Humanity, or any other spacefaring species, cannot be allowed to warp space recklessly. A governing body would need to establish and enforce warp lanes, toll specific, well-mapped routes through space that are deemed safe for travel, avoiding dense stellar regions, nebulae, and, most importantly, inhabited systems. These lanes would be the interstellar equivalents of shipping lanes in the ocean, designed to minimize environmental impact and the risk of collisions with other warp vessels or natural objects. Entering warp or dropping out of warp would likely be restricted to designated areas far from any planetary system, requiring hours or days of sublight travel to reach a planet, a necessary inconvenience for safety. The development and enforcement of these regulations would be a monumental political and diplomatic challenge. It would require a level of international, or rather, interstellar cooperation never before seen. Who has the authority to declare a warp lane? Who polices it? What are the penalties for a captain who takes a shortcut through a protected system? This could lead to the creation of an interstellar traffic control authority equipped with sensors to monitor warp signatures and patrol vessels to intercept violators. The ethical framework would need to be codified into law, perhaps something akin to a prime directive for environmental protection, stating that the natural state of space-time must be preserved whenever possible, and that any alteration carries a heavy burden of responsibility. Furthermore, the ethics extend to the discovery of other life. If we encounter another intelligent species, the use of warp drives near their worlds becomes an act of potential aggression or catastrophic negligence. Our mere arrival could inadvertently destroy their civilization if our warp bubble destabilizes their star or planet. This imposes a duty of extreme caution. Our navigation systems would need to be programmed to avoid any system showing signs of intelligence or even complex life, automatically rerouting to maintain a safe distance. The onboard AI would have to be deeply ingrained with these ethical protocols, preventing the crew from making a reckless decision in a moment of crisis or curiosity. The economic implications also tie into ethics. Would it be ethical for a corporation to operate warp freighters along the cheapest route if that route passes through a pristine region of space, potentially damaging it forever? Or should they be forced to take longer, more expensive routes along established lanes? This could create a system where green warp travel, which minimises environmental impact, is more costly, leading to economic disparities in access to interstellar trade. The very development of warp technology forces us to grow up as a species. We can no longer think in terms of conquering nature or exploiting resources without regard for the consequences. We must learn to see ourselves as stewards of a cosmos far more delicate and interconnected than we ever imagined. The empty space between stars is not a void to be conquered. It is an environment to be respected. Every activation of a warp drive is a decision that echoes through space and time. And we must be absolutely certain that the necessity of our journey outweighs the permanent scar we leave upon the universe. The pursuit of this technology, therefore, is not just a test of our engineering prowess, but a test of our wisdom, our foresight, and our capacity for ethical responsibility on a cosmic scale. Without this maturity, our first steps into the galaxy could be our last, as we render the very pathways we travel uninhabitable and dangerous, trapping ourselves in a web of our own making. The ecology of space-time is the final, and perhaps most humbling, frontier, teaching us that true exploration means leaving no trace, or at least minimizing the traces we cannot avoid leaving. It compels us to look beyond our own desires and consider the long-term health of the galaxy we wish to call home. This understanding must be baked into the very core of interstellar culture, from the education of future astro-engineers to the laws that govern the void. The challenges of building a warp drive are immense, but the challenge of using one responsibly is even greater, demanding a blend of scientific rigour, ethical clarity, and a profound respect for the silent, beautiful, and fragile fabric of the cosmos we are so eager to traverse. So, after considering the profound ethical and environmental costs of warp travel, we arrive at the most brutally practical question of all: who could possibly afford to build such a thing? The price tag for a single warp-capable cargo ship isn't just astronomical, it's galactic. A figure so large it ceases to have meaning in any economic system we recognise today. We are not talking about the budget of a superpower or a multinational corporation. We are talking about mobilising the entire industrial and resource base of a planet, or even a full solar system, for a project that would span generations. The sheer quantity of raw materials required is mind-boggling. Just the hull alone, forged from advanced composites and theorized materials like neutron star crust alloys, would require mining entire metal-rich asteroids or even dismantling small moons. The energy collection and storage systems, the continent-sized radiators, the network of quantum computers. Each of these subsystems represents a mega-project that would dwarf the combined construction of every skyscraper, ship, and plane in human history. This isn't just expensive, it's an endeavour that redefines the very concept of wealth and resource allocation. The common analogy is to the Kardashev scale, a method of measuring a civilization's technological advancement based on its energy consumption. A Type 1 civilization can use all the energy available on its home planet. A Type 2 civilization can harness the entire energy output of its star, building a single warp ship with its power demands equivalent to multiple stars, would firmly place its creators at the high end of a Type 2 civilization. This is a sobering thought. It means that until humanity, or any species, can effectively build a Dyson sphere or something similar to capture a star's energy, a warp drive is nothing more than a fantasy. The project is so vast that it cannot be funded through taxation or corporate profit. It requires a fundamental restructuring of society's goals and outputs. The economy behind this project cannot be capitalist as we know it. No company could shoulder the upfront costs with any expectation of a return on investment within a human lifetime, or even within a millennium. The venture capital model completely breaks down. Instead, the construction would have to be a coordinated effort of an entire species, a global or system-wide enterprise driven by something beyond mere profit. It might be motivated by existential necessity, like escaping a dying star, or by a unified, species-level dream of exploration. It would resemble the effort behind the Great Pyramids or medieval cathedrals, but on a cosmic scale, where the entire society is oriented towards this single, monumental goal for centuries. This raises immediate and profound political questions. What entity has the authority and the power to command such effort? Is it a world government, a technocratic council, a single, super wealthy individual who has effectively become the ruler of a post-scarcity economy? The concentration of power required to initiate and manage such a project is terrifying. The organisation that builds the Starship would, by definition, wield more economic and technological power than every other entity on the planet combined. This creates a massive risk of tyranny, where the needs of the many are sacrificed for the ambition of a few, all in the name of a glorious future. The purpose of the ship also becomes a critical point of conflict. Is it built for peaceful exploration and trade, or is it a weapon? A vessel that can deliver a continent's worth of resources can also deliver a continent's worth of bombs. The same technology that could seed life across the galaxy could also be used for planetary subjugation on an unimaginable scale. The political entity that controls the first warp drive effectively controls the fate of the solar system, and potentially everything within its reach. The logistics of labour are another nightmare. The workforce required wouldn't be in the thousands or millions, but in the billions, working across generations. Engineers, physicists, materials, scientists, and construction workers would live and die working on a project they would never see completed. This demands a social structure that can maintain motivation and stability over centuries. It would require a cultural narrative powerful enough to convince people to dedicate their lives to a blueprint, to have faith that their great-great-great-grandchildren will see the fruit of their labour. The societal stability needed is immense. A single major war or economic depression could derail the project for centuries, losing crucial knowledge and momentum. The sourcing of materials alone would reshape the solar system. We would move from planetary mining to asteroidal and planetary scale mining. We might dismantle Mercury for its iron core, or strip the atmospheres of gas giants for hydrogen fusion fuel. the very map of our solar system would be altered by the resource extraction, leaving behind a trail of industrial debris and reshaped worlds. This act of planetary engineering for a single ship highlights its insane cost. Furthermore, the project would necessitate technological advancements in every single field simultaneously. You cannot build the warp drive until you have the power source, but you cannot build the power source until you have the materials from the advanced mining operations, which themselves require advanced robotics and AI that don't exist yet. It's a circular dependency of epic proportions, where progress in one field is gated by progress in a dozen others. This suggests that the path to a warp drive isn't a single invention, but a slow, creeping ascent up the technological ladder, where each step enables the next, until the combined industrial and scientific base of the civilization finally reaches the critical mass where such a project becomes conceivable, if not easy. The economic model, therefore, would likely be a form of post-scarcity socialism for the essential workers, where their basic needs are met by the state or the building authority, and their compensation is a sense of purpose and a stake in the future mission. Currency, as we know it, might be irrelevant within the project's ecosystem. The medium of exchange would be energy, computational power, and material resources, all allocated by a central planning AI of unimaginable complexity. This AI would be the ultimate project manager, optimizing resource flows, managing the workforce, and solving the trillions of interdependent problems that would arise daily. In the end, the economics of building a warp ship tell us that it is not a product of a mature civilization, but the project that forces a civilization to mature. It demands that we overcome our petty squabbles, our short-term economic thinking, and our limited planetary perspective. It forces us to unite as a single species with a common goal, to learn to manage resources on a solar system scale, and to plan with a time horizon of centuries. The cost is not just in materials and energy, but in social and political evolution. The civilization that launches a warp ship is not the same civilization that started building it. It has been forged in the fires of this grand endeavour, emerging with the wisdom, unity, and power necessary to take its place among the stars. The price of a ticket to the galaxy is nothing less than the complete transformation of who we are, proving that the greatest barrier to interstellar travel may not be the physics of space-time, but the politics and economics of our own world. The project becomes a mirror, reflecting our ability to cooperate, to sacrifice, and to dream together across generations. Without passing this test, we remain forever confined to our cradle, looking up at the stars but unable to reach them, not because of a lack of engineering genius, but because of a failure of collective will and imagination. The true cost of the Starship is the birth of a new kind of human society, one capable of such a magnificent and terrible undertaking. So, after mobilizing the entire resources of a civilization to build this magnificent starship, we confront a terrifying irony. The very same technology that lets us conquer the galaxy might also prevent us from ever safely arriving anywhere. Because stopping a universe in motion is a physics problem of nightmarish proportions. You see, the warp drive isn't like a car where you just take your foot off the gas. It's a controlled, sustained distortion of reality. And undoing that distortion without destroying everything in the process is arguably more difficult than creating it in the first place. The core of the problem lies in the nature of the warp bubble itself. During travel, the bubble has been contracting space-time in front of the ship and expanding it behind, all while accumulating a dangerous amount of energy at its leading edge. A phenomenon often called the bow shock or pre-fire. Son, this isn't just heat. It's a concentrated buildup of high-energy particles and radiation, trapped by the distorted space-time geometry. If you simply shut off the warp field, all that pent-up energy is released in an instant, like popping a balloon filled with dynamite. The result wouldn't be a gentle stop, it would be a cataclysmic explosion, vaporizing the ship and potentially devastating any nearby celestial body, turning a promising new world into a scorched wasteland. Therefore, deceleration must be an incredibly gradual and meticulously controlled process, a careful unwinding of the cosmic knot you've tied. The proposed method involves a delicate reversal of the warp field emitters. Instead of contracting space ahead, the forward emitters would need to slowly reduce their effect, while the rear emitters would switch their function. Their job would be to begin contracting the space behind the ship, effectively creating a braking effect against the expansion that was propelling you forward. Think of it like trying to stop a car by carefully applying reverse thrust while also easing off the accelerator. But the car is a continent-sized object moving faster than light, and the road is the fabric of the cosmos. This reversal isn't a simple flip of a switch. It's a symphony of precision, requiring nanosecond adjustments to the power and polarity of thousands of individual emitters spread across the whole. The ship's AI would have to manage this process perfectly, balancing the decay of the forward field with the growth of the new braking field behind, all while monitoring the immense energy loads to prevent a feedback loop or a field collapse. The margin for error is zero. Any asymmetry in this process could cause the warp bubble to destabilize prematurely. If the bubble collapses unevenly, the ship could be violently ejected back into normal space. But here's the horror. The ship wouldn't just be moving at its sublight velocity, it would be carrying the momentum from its warp speed journey. The laws of physics are tricky here, but many theories suggest that upon bubble collapse, the ship would revert to a velocity relative to the local space-time, which could still be a significant fraction of the speed of light. Imagine being flung out of warp and instantly finding yourself travelling at 90% of light speed. At that velocity, even the sparse atoms of interstellar space would strike the hull with the energy of nuclear bombs, and any attempt to slow down with conventional thrusters would be futile, as the energy required is astronomical and the G-forces would be instantly lethal. The ship and everyone aboard would be vaporized in a flash of light, a brief, tragic footnote in the cosmos. Another catastrophic failure mode involves the accumulated energy in the bow shock. If the deceleration process is too abrupt, that energy might not dissipate safely. Instead of being gradually bled off, it could be focused and released as a directed energy beam or a massive shockwave through space-time itself. This wouldn't just destroy the ship, it could have collateral damage on a stellar scale. A miscalculated deceleration near a star system could send a wave of destructive energy washing over planets, stripping atmospheres, triggering global extinctions, or even destabilizing the star. You would have inadvertently turned your starship into a weapon of mass destruction, wiping out the very life you might have been sent to find or colonize. This places an enormous responsibility on the navigation and propulsion systems. The deceleration sequence must begin light years away from the target destination. A slow, days or weeks-long process of carefully winding down the field. The ship's sensors would need to constantly scan the space ahead, not for obstacles, but for any gravitational influences that could perturb the delicate balance of the warp field during this vulnerable phase. A passing star's gravity, or even a dense cloud of gas, could introduce fluctuations that the AI must instantly compensate for. The power management during deceleration is another Herculean task. The braking emitters require colossal amounts of energy, comparable to the initial acceleration, placing a massive strain on the ship's reactors. This energy demand must be balanced against the needs of life support, navigation, and defensive systems, all while ensuring that the reactors themselves don't overload from the sudden shift in power draw. The heat generated by this process is equally immense, requiring those continent-sized radiators to work at maximum capacity to prevent the ship from melting from the inside out. The crew's role during this phase is largely one of supervision and trust. They would be monitoring the AI's progress, watching a cascade of data streams that indicate field stability, energy levels, and trajectory. It would be a time of intense psychological stress, knowing that a single red light on a console could mean the difference between a successful arrival and utter oblivion. There is no room for manual override. The reactions required are too fast for human reflexes. The crew must have absolute faith in the machine intelligence guiding them. Furthermore, the deceleration process must be perfectly calibrated for the ship's mass and velocity. A ship carrying a full load of cargo would decelerate differently than an empty one. The AI must account for this in real time, adjusting the emitter strengths and sequences accordingly. This requires a deep, integrated understanding of the ship's current state, something that must be constantly updated through a network of sensors monitoring stress, mass distribution, and power flow throughout the vessel. The software controlling this is perhaps the most complex ever written, a masterpiece of predictive algorithms and adaptive control systems. It must be able to learn from minor anomalies and adjust its models for future decelerations, because no two journeys will be exactly alike. The interstellar medium, the gravitational landscape, and the ship's own condition will always present new variables. The consequences of failure are so absolute that the deceleration system would need layers upon layers of redundancy. Multiple independent AI cores would cross-check each other's calculations. Backup power systems would be ready to engage instantly if the primary reactors falter. The emitter array itself would be designed with overlapping fields so that the failure of a few individual units wouldn't cause a total collapse. This entire apparatus, the braking emitters, the control software, the power buffers, adds yet more mass, complexity, and cost to the already monumental ship, but it is non-negotiable. Without a safe and reliable method for deceleration, the warp drive is nothing more than a suicide engine, a one-way ticket to a fiery end. This challenge forces us to reconsider the very purpose of the journey. Is it worth the risk? The deceleration problem encapsulates the ultimate dilemma of interstellar travel. The power to cross the void comes with the responsibility to control that power with godlike precision at both ends of the voyage. It's a humbling reminder that our ambition to reach the stars is matched only by the universe's relentless physics, which demands perfection from us every step of the way. The development of a solution will require not just advances in physics and engineering, but a profound commitment to safety and foresight, ensuring that our first greetings to new worlds are not explosions but peaceful arrivals, a careful and respectful entry into someone else's sky. So, after navigating the terrifying physics of stopping your starship, you might think the challenges are over. But we now venture into the most mind-bending and fundamentally unsettling territory of all, the problem of time itself. You see, by travelling faster than light, even via a warp bubble that cleverly sidesteps conventional acceleration, you are playing with fire in the domain of causality, the fundamental rule that cause must always come before effect. This isn't just a theoretical curiosity. It's a potential showstopper that threatens the very logical consistency of the universe. And by extension, the possibility of your journey. The most famous illustration of this is the grandfather paradox. Imagine your warp ship is so fast that it can travel to a point in space that, from another perspective, is in your own past. You get out, and before your own parent is born, you accidentally prevent your grandfather from meeting your grandmother. So, you are never born. But if you were never born, how could you have travelled back in time to prevent the meeting in the first place? This is a logical contradiction, a loop that breaks reality. Now, you might think that since the ship itself isn't moving through local space, it's safe. But the problem is about the connection between different points in space-time. According to Einstein's theory of relativity, space and time are interwoven into a single fabric, When you manipulate space so drastically that you effectively arrive at a point before a light signal you emitted could get there, you have created a closed time-like curve, a path through space-time that loops back on itself. An observer watching your journey from the outside might see you arriving at your destination before you even left. From their point of view, this shatters the universal sequence of events. It means that an effect could, in principle, happen before its cause. Information could be sent into the past. The implications are terrifying. History could be rewritten, not through intention, but as a simple byproduct of your navigation. The foundations of physics, which rely on a clear, linear progression of time, would be invalidated. So, how could we possibly build a warp drive without breaking the universe? The engineers and physicists designing this system wouldn't just be worrying about fuel and hull integrity. They would have to become architects of causality itself. The solution wouldn't be a physical shield, but a software protocol, DOT, a set of causal protection rules deeply hardwired into the ship's navigation AI. This system would be the ultimate safeguard, a cosmic traffic light that prevents the ship from ever taking a path that could lead to a paradox. The first and most straightforward method would be to impose severe restrictions on potential routes. The navigation AI would have access to a map of the galaxy that isn't just about stars and planets, but about their positions in space-time. It would calculate the light cone for every possible destination, the region of space-time that can be reached from a given point without exceeding the speed of light. The warp drive would be programmed to only plot courses that keep the ship firmly within its forward or future light cone from its point of origin. It would refuse to compute a trajectory that would result in an arrival time that dot, in any valid reference frame, precedes the departure time. This implies that the universe itself may have a topology that makes some paths safe and others forbidden. There might be natural causal horizons or chronology protection features built into the geometry of space-time. Some theoretical models, like the concept of a cosmic censorship hypothesis, suggest that nature abhors paradoxes so much that it prevents them from forming, perhaps by making the energy requirements for creating a time loop infinite, or by collapsing the warp bubble whenever such a path is attempted. The ship's sensors would need to be able to detect these subtle features of space-time, mapping the causal structure of the galaxy in real time to avoid these dangerous zones. This adds an entire new layer to navigation. It's not enough to know where a star is. You have to know its causal relationship to your current position in space-time. The navigation AI would be making calculations based on general relativity on the fly, solving complex field equations to ensure every course correction maintains causal integrity. Another theoretical idea involves the concept of quantum reconciliation. This suggests that if a paradox were about to occur, the universe would simply not allow it, resolving the inconsistency through some quantum mechanical process. But from an engineering perspective, relying on this is like relying on a fuse to blow in a circuit. You'd rather not overload the circuit in the first place. The ship's systems would be designed to be proactively causal, not relying on a cosmic safety net. This has profound implications for the crew and the mission. The navigation I would have ultimate authority over the flight path. A human captain could not order a course that violates these protocols. The I would simply refuse to execute the command. The crew would have to accept that their freedom to go anywhere is limited by the fundamental laws of causality. This might mean that certain seemingly straightforward journeys are impossible because they would create a closed time-like curve. You might be able to travel to a star 100 light-years away, but you could never travel to a point from which you could see your own launch with a telescope, because that would require the light from your launch to have already arrived there. The very concept of now becomes relative and navigationally significant. The development of such a causal protection system would require a deep integration of quantum gravity theory into practical engineering. We currently lack a complete theory of quantum gravity, so this represents another monumental scientific hurdle that must be overcome before a warp drive can be deemed safe, not just for the crew, but for the logical consistency of reality. It means that the software engineers writing the navigation code are, in a very real sense, writing laws of physics into their program. The system would need to be invulnerable to hacking or corruption, as a malicious actor who disabled the causal protocols could theoretically attempt to manipulate history with unknowable consequences. Furthermore, this problem connects back to communication. If you could send a message via a warp bubble or some other FTL method that arrives before it was sent, you create the same paradox. This reinforces the idea that any FTL technology, for it to be consistent, must be governed by strict causal rules that prevent information from looping back in time. In the end, the problem of time paradoxes forces a humbling conclusion. The universe may not be an open playground for our ambition. It may have built-in roads and one-way signs woven into the fabric of space-time itself. The ultimate challenge of building a warp drive may not be generating the power or finding the exotic matter, but in obtaining the wisdom to use it without breaking the clockwork of causality. It suggests that the universe permits such travel only along certain safe routes, turning the galaxy from a wild frontier into a structured network with strict rules of engagement. The dream of flying anywhere we want, anytime we want, might be an illusion. Our path to the stars may be channeled along rivers of safe causality, and learning to read those currents will be the final and most profound skill we must master. The warp drive, therefore, becomes not just a tool for exploration, but a key to understanding the deepest structure of reality, teaching us that time is not a river we can row upstream, but a delicate and protected thread in the cosmic tapestry that we must learn to navigate with reverence and care. So, after ensuring our journey doesn't break the laws of causality, we must confront a more visceral and immediate danger, one born not from physics, but from human nature itself: the threat of piracy. A ship carrying the resources of an entire planet is the ultimate prize, a floating fortune that would make every pirate in history green with envy, and in the lawless vastness between stars, you can be sure that someone, somewhere, will try to take it. This isn't about swashbucklers with cutlasses. It's about highly organised, technologically sophisticated criminals or rival factions who would see your vessel not as a marvel of exploration, but as the biggest score in the galaxy. Defending against such a threat requires a security paradigm that goes far beyond simple shields and weapons. It demands a holistic, multi-layered defense system that is as advanced as the warp drive itself. The first and most obvious line of defense is formidable physical and energy-based weaponry. Think beyond laser cannons. We're talking about particle beams that can disintegrate matter at a molecular level, plasma projectors that fire contained balls of star-hot fury, and perhaps even gravitic weapons that can crush enemy ships by manipulating local space-time. But these are almost a last resort. The primary goal is to deter and disable, not necessarily to destroy, as a destroyed pirate ship is still a cloud of debris you have to avoid, and the ethical implications of lethal force in interstellar space are complex. Therefore, the defensive systems would likely include non-lethal options as well. Imagine EMP emitters that can fry an attacker's electronics without harming the crew, or sophisticated jamming systems that can disrupt their sensors and communications, leaving them blind and disoriented. But the most critical component of defense would be the shields. These wouldn't be the glowing, bubble-like fields of science fiction, but intense, layered barriers of energy. The outermost layer might be a plasma shield, a swirling curtain of magnetically confined superheated gas that vaporizes incoming projectiles and diffuses energy weapons. Behind that could be a gravitic shield, a zone of distorted gravity that bends incoming fire away from the hull, acting like permanent active armour. These shields would require immense power, drawing directly from the main warp core, and their strength would have to be dynamically adjustable, channeling more energy to the point of impact in milliseconds. However, a pirate worthy of the name would come prepared with shield-piercing weaponry, perhaps phased tachyons or other exotic particles that can bypass conventional defences. This is where active countermeasures come into play. The ship would need a point defence network, a swarm of autonomous turrets that can track and destroy incoming missiles, torpedoes, or boarding pods with pinpoint accuracy. These turrets would be controlled by a dedicated combat AI, a subsystem of the main computer that can make thousands of targeting decisions per second, prioritizing threats based on their trajectory, energy signature, and destructive potential. But the most fascinating and complex aspect of interstellar security would be counter-warp warfare. A clever pirate wouldn't just attack you in normal space. They would use warp technology against you. They could generate localized warp interdiction fields, creating bubbles of distorted space-time that prevent you from entering warp, trapping you in a system. They might deploy warp mines, dormant devices that create a micro-warp bubble collapse when a ship passes nearby, simulating a catastrophic drive failure. Or they could use warp spoofing, projecting false sensor signatures of non-existent ships or celestial bodies to confuse your navigation AI and lure you into a trap. To counter this, your ship would need its own suite of counter-warp measures. This could include the ability to generate warp static, a broad-spectrum emission that disrupts the formation of warp bubbles in a local area, effectively creating a no-warp zone around your ship to prevent enemies from warping in too close. It might also have warp echo sensors that can distinguish between a real celestial object and a holographic projection created by warp field manipulation. The most advanced countermeasure might be the ability to generate short-range, defensive warp pulses, brief, controlled distortions that nudge incoming warp-based threats off course or destabilize them before they can reach you. All of these systems, from the plasma shields to the warp spoofing detectors, generate an ocean of data. This is where cybersecurity becomes paramount. The brain of the ship, the super-intelligent AI, is the most valuable target. A pirate who could hack into your systems could disable your weapons, lower your shields, open your airlocks, or even commandeer the warp drive itself. The cybersecurity protecting the AI would have to be impenetrable. We're talking about quantum encryption that changes its key with every transmission, biometric and neural link authentication for all command-level access, and perhaps a decentralized hive mind architecture for the AI itself, so that even if one node is compromised, the others can isolate it and maintain control. The AI would constantly be running penetration tests on its own systems, looking for vulnerabilities and patching them in real time. It would have to be capable of recognizing sophisticated social engineering attacks aimed at the crew, warning them if a communication seems suspicious. The human element of security is just as crucial. The crew would include a dedicated security team, highly trained in zero-gravity combat, boarding action defense, and crisis management. The ship's internal design would incorporate choke points, blast doors, and security stations to slow down any boarders who make it through the external defences. The crew would be drilled relentlessly on emergency protocols, from repelling boarders to dealing with internal sabotage. The psychological profile of pirates is also a factor. They could be desperate fugitives, state-sponsored privateers, or even a rival corporate entity using deniable assets. Understanding their motivation is key to anticipating their tactics. A desperate pirate might launch a reckless all-or-nothing assault, while a state-sponsored one might use more subtle electronic warfare to disable and capture the ship intact. This requires the ship's AI and command crew to be adept at threat assessment, analysing the behaviour of an unknown vessel to determine its intentions long before it enters weapons range. Furthermore, the very nature of warp travel complicates defence. If a pirate ship can warp in unexpectedly, the reaction time is effectively zero. This means the ship's defensive systems must be in a constant state of alert, with sensors actively scanning not just normal space, but also monitoring the subtle ripples in space-time that hint at an impending warp arrival. The AI must be able to identify a hostile warp signature and activate shields and weapons before the enemy ship has fully materialized. The economic cost of these defensive systems is staggering, adding another layer to the already immense price of the ship, but it is a necessary cost. Without such defences, the ship is a sitting duck, a treasure chest waiting to be plundered in the dark. The development of interstellar security technology would likely proceed in lockstep with the development of warp drive itself, a perpetual arms race between builders and pirates. In the end, the security of an interstellar cargo ship is a testament to a grim reality. Wherever humanity goes, its darker impulses follow. The dream of peaceful exploration is shadowed by the need for formidable self-defense. The ship must be a fortress, a battleship, and a vigilant guardian, all while fulfilling its primary mission of transport. This complex, multi-layered security apparatus underscores that the final challenge of interstellar travel isn't just about surviving the universe, but about surviving each other. The void may be empty, but it is not safe. And the greatest threats may not be cosmic radiation or gravitational anomalies, but the deliberate, calculated aggression of those who see your incredible achievement as nothing more than a target. So, after centuries of service, having evaded pirates, navigated cosmic hazards, and crossed the galaxy countless times, even the most stalwart starship must eventually face its final voyage. Not through space, but through time itself. What becomes of a legendary vessel when its warp core grows cold and its intelligent hull shows its age? You can't just park it in a cosmic scrapyard or abandon it in a stable orbit. A derelict the size of a city would become the single greatest navigational hazard in any star system. The ghost ship with the mass of a mountain, silently drifting and waiting for some unlucky freighter to collide with it at relativistic speeds. The end of a starship's life is a problem of decommissioning on a scale we can barely imagine, a project almost as complex and costly as its original construction, and it forces us to think in terms of legacy and long-term consequences that span generations. The most straightforward and yet most daunting option is systematic dismantling in a specialised orbital dry dock. This wouldn't be a simple operation. It would be a deconstruction project lasting decades, a reverse engineering of the monumental effort that built it. The same fleet of robotic maintenance drones that once repaired the ship would now be reprogrammed for careful disassembly. They would begin by safely draining and containing any remaining exotic matter from the warp drive emitters, a process requiring extreme caution as this material is inherently unstable. Then, they would methodically detach and catalogue every major component: the quantum computer cores, the plasma thrusters, the continent-sized radiator wings. Each would be carefully removed. The valuable materials, the neutron star alloy girders, the carbon nanotube weave of the hull, the rare elements in the sensor arrays, would be sorted and sent to recycling facilities to be melted down and repurposed for new construction projects, perhaps for the next generation of starships. However, the energy and infrastructure required for this are immense. You need a dry dock facility large enough to hold the ship, and the process consumes vast amounts of power. It's a massive industrial undertaking that only makes economic sense if the recycled materials are incredibly valuable, which they are. But the upfront cost of the deconstruction is staggering. This raises the question, who pays for it? The original owners may be long gone, their corporation or government dissolved into history. This implies the need for an interstellar decommissioning fund, a kind of cosmic pension plan for starships, where a portion of the ship's earnings over its lifetime is set aside to pay for its eventual recycling. The second, more poetic option is repurposing, giving the old vessel a new life and purpose. Instead of being torn apart, the ship could be towed to a young, developing star system that lacks infrastructure. There, it could be seeded. Its massive hull could become the foundational core of a new orbital habitat, a ready-made space station around a virgin world. The crew quarters and life support systems could be refurbished to house the first wave of colonists, providing immediate, robust shelter. The warp drive itself would be deactivated and perhaps studied as a historical monument, but the ship's power plant, even at a fraction of its original output, could provide energy for a growing settlement for centuries. The cargo holds, once filled with ore and goods, could be converted into hydroponic farms or manufacturing centres. In this scenario, the starship becomes the literal seed of a new human outpost. Its legacy, not one of travel but of roots. It transitions from a nomad to a cornerstone of a new civilization. Another form of repurposing could be for terraforming. If the ship is towed to a barren but promising planet, its final mission could be a controlled crash landing. This would, of course, require meticulously stripping it of any hazardous materials first. The impact itself would deliver massive amounts of pre-processed metals and minerals to the planet's surface, and the wreckage could form an artificial reef or the foundation for a future city. More advanced ideas might involve using the ship's old reactor in a final, controlled meltdown to release heat and gases into the planet's atmosphere, kickstarting a greenhouse effect. This is a dramatic, violent end, but one that gives birth to a world. The choice of how to decommission a ship would depend heavily on its condition, its historical significance, and the needs of the era. A ship that fought in famous battles might be preserved as a museum, towed into a permanent orbit around its homeworld as a testament to engineering and courage. Though maintaining such a vast relic against the ravages of time and micrometeors would be a perpetual expense. A ship that suffered a catastrophic systems failure might be too dangerous to repurpose and would have to be carefully dismantled in a remote, designated ship graveyard system far from any traffic. The entire life cycle of the ship, from its conception to its final rest, is a story that spans generations. The engineers who laid its keel would never see it decommissioned. The children born during its construction might live to see it retired. This long-term perspective forces a culture of stewardship. You don't just build a ship for today, you build it with its end in mind. This influences design choices from the very beginning. Modular construction becomes key, so that parts can be easily replaced and eventually disassembled. The use of standardized, recyclable materials is prioritized. The ship's AI, containing the sum total of its experiences, might be archived as a historical record, a digital ghost of a great explorer. The decommissioning process is also a final test of the society that built it. Does it have the responsibility and the resources to clean up after its greatest creations? Or does it leave its trash in the cosmic backyard? A civilization that carefully manages the end of its starships demonstrates a maturity and a respect for the universe it inhabits. It shows an understanding that our creations have a life beyond our own, and that our responsibility to them doesn't end when their primary mission is over. The legacy of a starship is therefore twofold: the journeys it completed and the future it enables after its travel is done. Whether it becomes the skeleton of a new space station, the foundation of a new world, or simply returns its atoms to the industrial cycle to be born again as a new ship, its story never truly ends. It simply enters a new chapter, a quieter one, but no less important. The cycle of creation, service, and renewal is what allows a spacefaring civilization to sustain itself, ensuring that the wonders of one age become the building blocks of the next. The final problem of building a starship, then, is not how it begins, but how it ends. And in solving that problem, we learn the ultimate lesson, that true greatness lies not just in the journeys we undertake, but in the legacy we leave behind.